Hello and welcome to our crash course for research methods in psychology. We are going to be discussing a lot about the scientific method and about how research is done in contexts for psychology, although many of the things that we're going to learn in this course have equal applications in other scientific disciplines. Chapter 1 is kind of an overview. We're going to be looking at a lot of vocabulary terms and hopefully kind of set you up a little bit for some of the more complex chapters as we discuss a little bit later on. First of all, some basic stuff about research methods and how they apply. First of all, behavior means any overt activity of a person. Typically, when you're talking about psychology and you're talking about research methods, you are studying a behavior. A behavior could be something intentional, a behavior could be something unintentional, it could be something ingrained, it could be something that is a response to stimuli, it could be something that's an instinct. Behavior can be pretty much anything. Research could be applied research or basic research. Applied research is when you do research in order to try to solve a real-life problem. Research to find a safer type of tire, or a more fun type of video game, or a better tasting ice cream, or whatever it is. That's applied research, something that you're trying to find something that has a real life application. Another type of research, also important, is basic research, which is really driven purely by curiosity and a desire to expand knowledge, which essentially is the idea of gathering information just in order to understand human behavior. Maybe not necessarily to directly apply it, although basic research very often leads to applications, but the study of why people develop phobias might be a basic research question. And then later on, when you take those results and try to figure out a cure or how people can be prevented from developing these phobias, then you would cross over into the domain of applied research. A critic is a person who makes informed judgments. Hopefully you are a critic. I like to try to be a critic when I can. A critic doesn't necessarily mean somebody who is critical in terms of disparaging of things. Critic doesn't necessarily mean a scientist. A critic simply means anybody who makes informed judgments. And one of the goals of this course is to make you into a critic. Yes, believe it or not. Goals of psychological research, and this is really more of kind of a general synopsis of experimental ideas. In fact, I'm going to change the title. You're going to see me change things every once in a while as we move on with this course. Now, when an experiment is run, and of course experimenting is a way to test a hypothesis. The way the scientific method works, and we're going to go through all this many times, but the way the scientific method works is essentially first you come up with some sort of a problem. What is it that you're looking to do? For example, you're looking to become warm on a winter day. Then you test a hypothesis, or you establish a hypothesis based on your observations. Your hypothesis is that by wearing a heavier a coat you wear, the warmer you're going to be. Then you have to design some sort of an experiment. And an experiment has a control variable and an independent variable and a dependent variable. The independent variable is the thing that you're testing. For example, in my example, the independent variable would be the thickness of the coat that you're wearing. The dependent variable, on the other hand, is the effect that you're testing. For example, in my example, where the independent variable is the size of the thickness of the coat that you're wearing, the dependent variable is how warm you are. My hypothesis was that a heavier coat is going to make me warmer, so therefore the independent variable is the coat, or how heavy the coat is, how thick the coat is, and the dependent variable is what the effect is in terms of keeping the person warm. The control variable, on the other hand, is the thing to establish a baseline of expectations. A control variable is something that you don't apply the independent variable to be able to have a basis for comparison. For example, if I'm testing whether a coat will work to keep somebody warm, a control group, or a control person, a control, would be a person that doesn't wear any coat at all. You put a person outside in the freezing cold without a coat, and that person is probably going to be cold. That person is the control. Then you give the other person, the experimental group, the person that's being experimented on, you give that person a coat. And maybe you give another person a thicker coat, and another person an even thicker coat. But the control variable, or the control group, or the control subject, the control person, is the person to whom you do not give anything that you're testing on to establish a baseline of behavior, or a baseline of effect that would apply if you didn't give any of the independent variable to. Here's an example. If you want to test the effectiveness of cholesterol-lowering medication, you can give 100 people with high cholesterol no medication. That is the control group. Then you can give another medication A and another medication B. You've really got three things that you're testing. You have the control group, that is the people that you give nothing to. You've got two experimental groups. The one that you give medication A, that's the experimental group for medication A. Then you've got medication B, the people that you give medication B to. And so that's the independent variable. The dependent variable is later on, after a few months or whatever it is, you measure the effect of each independent variable. If the person, for example, if all three groups did the same, the control group and A and B had approximately the same results, you might conclude that neither medication does anything because they did essentially the same thing as nothing did. If the medication A group works and medication B group doesn't, or you have the control on one level and with medication B and the medication A is higher, you may conclude the medication A works and medication B doesn't. If A and B both do better than the control group, you might conclude that they both work. If medication A does wonderfully and medication B does okay and the control group does terribly, well then you may conclude that medication B does something, but medication A is even better. So then there are, of course, other variables that you want to control for. For example, you don't want to bring in, when you're doing an experiment for cholesterol lowering medication, you don't want to bring in one group full of 25-year-olds and the other group full of 65-year-olds, because then you could have other variables, which are sometimes referred to as confounding variables, which tend to skew it by having alternative influences. People that are older may have a more difficult time lowering their cholesterol than people that are younger. People that are heavier might have a more difficult time than people who are lighter. So you want to try to keep everything else pretty much the same. Have the control group be the same as the experimental group in terms of their age, in terms of their weight, in terms of their mood, in terms of whatever other variables you can think of to control, and have the only distinction between the two groups being whether you give the independent variable, whether you give the medication in our case. And the thing that makes this course interesting and an experiment challenging is that you've got so many different factors that you have to watch out for. One of these factors is something known as the Stroop effect. The Stroop effect essentially is a takeoff on the power of suggestion, and the idea that what somebody is told will work has an effect on the person's mindset, and therefore has an effect on what actually happens in terms of the way we feel about things and the way we do things. If you look at this example over here, right where my cursor is here, the top, if you pause it and do it yourself, I think it's fairly apparent that it's a lot easier for me to read green, red, blue, purple, because the words are the same as the color, whereas over here, reading blue, purple, red, green, purple, green, I can do it if I think about it for a second or two, but it's much less intuitive, because when I see this, I see a red color, and establishing that in my mind as blue it doesn't take very long, it takes a fraction of a second, but it's still a little bit harder than it is along the top, again, because you're more prone to suggestion based on what you see. And these things have an effect on how even things like medication might work based on this idea of the power of suggestion. Where do people get their research ideas? Well, the first part of any scientific process is observation. Look around. Before you even develop your hypothesis, actually really the first step before even here is having a problem, what it is that you're looking to solve. Look around based on your own observations, based on your own experience. You need to develop a hypothesis. A testable hypothesis specifies how two or more variables are related. For example, taking vitamin C will cause me to get fewer colds. Well, that's two different variables. Taking vitamin C is a variable, whether I take it or don't take it, or take 1,000 milligrams or take 100 milligrams or whatever. These are all different possibilities. And then there's how many colds I get. That's another variable. All a hypothesis means is there is a relationship between two different variables. Then I experiment in order to make a determination as to whether my hypothesis was correct. And then, based on the results of that experiment, I could establish a theory or even a law. A theory is something that is proven to be probably true by experimentation. A law is something that's definitely true. It's a mathematical truth. In science, you're usually dealing with theories. When it comes to law, you're really dealing more with mathematics. We pretty much know that 2 plus 2 is 4. We don't really have to have a theory about it. With science, things aren't really 100% sure. We're dealing more with theories. But, you still have laws. For example, you've got Newton's laws of motions. You've got Kepler's laws. You've got the laws of thermodynamics. These are things that are not subject to dispute. You've got theories which seem to be scientifically proven but may not be 100% true. The theory of evolution and various other theories that apply. The Social Science Citation Index is a tool for researching psychological literature and help to make sure that things are reliable. It's established and published and available to people doing psychological research. A pilot researcher study is the thing that we're going to be looking at on the next slide over here. A pilot research or pilot study is a small-scale preliminary study to evaluate feasibility. If I want to do a massive study in terms of why people become depressed, to figure out why are people afraid to fly in airplanes, or whatever it is, I may not, and I think in order to really do this right, I need 100 participants, and I need a budget of $5 million, and I need 12 workers, and I need this, that, and the other thing. To establish that we can actually do it and that the methods that we are anticipating will actually work, we may want to run a pilot study or a pilot research where you just get a few people together and just run a very quick study, not necessarily to get your final answer, but just to look at your methods and refine your methods and establish that these methods are going to work. Pilot research is often used to determine whether or not the levels of an independent variable are appropriate. Whatever it is we're testing, is it safe, first of all? Maybe a pilot study to see if we're planning on giving this certain amount of medication to 1,000 people. Well, maybe let's try it on 3 people first, and see if there are some major safety problems. Or will this be the sort of thing that people will continue with the study? If we see that everybody is miserable, all the participants are miserable, and they drop out, well, then you'd rather find that out at the beginning when you're trying it on 5 people and spend a couple of $1,000 on it, than when you're trying it on 200 people and have spent $1 million on it. A pilot study is something that's used with a very small sample size, and that's a problem in pilot research. So really, from pilot studies, you're not really able to gather final conclusions and establish theories, but you can establish that maybe there's a reason to believe that your study might work and that the study is in fact feasible. Then we've got some pitfalls that are relevant to research methods, and these are things that you have to watch out for. These are things that could ruin experiments and negate potential information. There could be deliberate fabrication. If a scientist believes that in order to get funding they have to come to a certain conclusion, then you can deliberately fake data. That obviously ruins whatever data there might be. Or there could be inadvertent bias. It could be because the researcher wants something to come a certain way for funding purposes, or simply because the researcher thinks at the beginning of the experiment that this is the way the result ought to come out, and therefore doesn't pay enough attention to the possibility that he or she is wrong. That can subtly, even though the scientific method should be pretty free from bias, because the scientific method is very clear steps in terms of what is appropriate and what is inappropriate, still, things on a much more subtle level can be ruined by researcher bias. And of course, there are many different ways in which you can try to overcome these pitfalls. For example, have many scientists research the problem in different ways. Well, then it's much less likely that the research of an individual or a small group is going to affect it altogether. Also, using a protocol, using a specific series of steps. Even if my bias, if I'm trying to do an experiment and I'm worried about my own subtle bias affecting the way I do the research? Well, laying out clearly the terms of what I'm going to do and how I'm going to do it and following those steps precisely minimizes the chance that whatever bias I have is going to impact the way I do things. There's this also another problem called anthropomorphizing, which is ascribing human qualities to non-humans, and that could be a problem in terms of research based on the idea, drugs don't necessarily want to establish a cure. Things that are studied by scientists, most of the time, we tend to think of things as human beings, whereas things being tested are obviously not humans and don't have human emotions and human tendencies, and we have to kind of divorce the tendency of things to happen from the way we would want them to happen as human beings. Then there are some other aspects regarding factors in experiment. Number one is a placebo. A placebo is a pharmacologically inert substance, which means it does nothing. For example, if I want to test whether a headache medication works, well, if I just give 10 people the medicine, and 10 people I give nothing to, and the 10 people that I give the medicine to do better, it's possible that it had nothing to do with the pill itself. It's just possible that the people thought that they were getting medicated, and therefore they felt better about themselves and they felt better about their treatment. That is a real psychological effect. Sometimes just the fact that people think that they're being treated is enough to actually get them a little better. I mean, that's a powerful psychological idea in general, but when you're testing it, you want to try to make sure to negate that possibility if you really want to test whether the drug is actually doing anything. And one way to do that is to use a placebo. A placebo is where instead of giving just 10 people the medicine and 10 people nothing, you give 10 people the medicine and the other 10 people, the control group in other words, the experimental group you give the medicine to, the control group you give them something that looks like the medicine and tastes like the medicine and feels like the medicine, but in fact is just a sugar cube, a sugar pill, and so the people that take it don't know one way or the other. The people that are in the control group, the people that are not getting the medicine, are getting what are called placebos. You can also do what's called a double-blind experiment. Most experiments in this regard, the doctor knows which people are getting placebos and which person are getting the real medicine. That's called a single-blind experiment. The doctor knows, or the experimenter knows what's going on, but the patients don't. On the other hand, sometimes you can have a double-blind experiment, which is even better, because the person that's giving the pills doesn't even know which ones are getting the placebo and which ones are getting the actual medication. The reason why this is better is because if the doctor doesn't even know which people are the experimental group and which people are the control group, the doctor can't unintentionally give some. Maybe the patients will be able to pick up a sense from the doctor that he or she is just getting a placebo. They're based on the doctor's behavior. But if the doctor doesn't even know, then the doctor obviously can't give it away. A couple of more quick ideas regarding research methods. Operational definition is a definition that allows other people to apply the same concept. It should be concrete and measurable. Whenever you establish a relationship or establish a rule or establish really pretty much anything, it should be phrased in a way that allows other people to understand in the exact same terms that you do and be able to recreate your experiment and recreate whatever it is that you're applying. And finally, to be shown by experimentation, a conclusion has to be measurable. You can't, for example, show that a person who takes this will be in a better mood. The person who takes this pill will be nicer. The person who takes this steroid will be fastest. Well, how do you... Well, actually, fastest does work because fastest is measurable. You can see how when two people run something, you can tell which one is faster. You can't really measure how nice a person is. You can't really measure how good something is. You can't necessarily, measure whether it smells nice. You can measure quantity. And so experiments, rather than saying this experiment proved that this food tastes good, you can say that this experiment proved that adding this food additive caused 12% more people to say that they enjoyed the taste afterwards. That's something that's quantifiable. That's something that's measurable, rather than just saying something in a more abstract way. Chapter 2 continues with various vocabulary words when it comes to research and just concepts that are specifically relevant to research. And these are all the common thread through this chapter is these are things that scientists and people who are doing research have to watch out for when when determining results, when making sure that they're able to understand what the results might imply. Okay, so first of all, you got this idea of social loafing, which is that people work less when in a group because they rely on each other. That's the general idea that just because you bring four people to do a job doesn't mean they're not going to be four times as productive as an individual would. Sometimes four individuals working together might only be three times as productive as an individual work because people kind of rely on each other. If you have one person, that person knows he or she better do the whole job or it's not going to get done. If you have four people, tend to, a little subconsciously think that the other people are going to do it, so I don't have to worry about it. Method of authority is a belief in something that we attain because we trust the source. Sometimes somebody tells you, a parent, a teacher, or somebody whom you trust tells you something, we take it as a given even though it may not actually be proven. These are all things that are really stand contrasted with the scientific method where everything needs to be proven or else scientists don't necessarily believe it. Faith is also believing in something that was asserted but you have not seen direct evidence. You believe it's universe works in a certain way, whatever the case may be. That could be based on faith, even though there's no specific evidence for it. And then there's tenacity, which could even be dangerous. Tenacity is continuing to believe something, even if it's proved that it's not true. In some contexts, like the context that I have an example over here, tenacity sounds good. I still believe that people are good, even if you hear stories of mass murder. That's a relatively benign example, but tenacity can also be a situation where people, even though something has been disproven, even though something has been proven to be false, people still believe it because they want to believe it or for whatever other reason. Now let's look at some methods of data collection. And data collection and methods of understanding things. One possibility, one method that's really not the scientific method, a method that's always exists, is the a priori method. And the a priori method is something that you know to be true, even though it hasn't been proven, just based on logic. Based a priori, you have a prior understanding of something, and based on that, you believe it to be true, even though it cannot be proven. So, for example, if a person was home all day, you know that the person was home at a given time during the day. In other words, just applying a general rule to a particular situation, even though you're not proving that particular situation to be correct. A priori, I know that it's daytime outside during, between the hours, let's say in the summer, between the hours of 5 a.m. and 9 p.m. And so therefore, I know that at noon the sun was out, or not, maybe not the sun was out, but it was light out. I know that it was light out at noon. Now, it's certainly a valid way of reasoning, but it certainly is not specifically proven. I didn't prove with scientific evidence using the scientific method that it was light out at noon. I just know that it was light out at noon because I know that that's the way it always is. It's kind of taking a general rule and applying it to a specific case. The scientific method, on the other hand, which again is something that we use much more than the a priori method in terms of research, simply because when we test things, we're not testing things that we know. I mean, when we deal with whether it's going to be light out tomorrow at noon, we use the a priori method without thinking about it because we know what the rule is. We don't need to use the scientific method, we just simply know it. When we're dealing with research, we don't really know to begin with what the result is going to be, therefore we need to use the scientific method. And the scientific method relies on systematic observation, empirical observations, which means observations that can be measured, observations that can be defined in terms of numbers. 27% of people said that they got relief from their headache. 12% of people were able to run faster. Whatever. These are observations, and of course we rely on data. Data is information resulting from systematic observations. We test things, we experiment on them, and we gather the information and are able to use that information. Scientific research also relies on this idea of reasoning. Reasoning means drawing conclusions that are legitimate based on the rules of logic. There's deductive reasoning and there's inductive reasoning. Deductive reasoning means you take a bunch of individual observations and combine it to establish a general rule. You deduce a general rule. First you gather the information, and then you draw conclusions that arise from the data. I gathered the information that every day in July the high temperature was somewhere in the 80s or 90 in the 80s and the 90s, and therefore I deduce a rule that in July it's hot outside during the day. Doesn't have to be that complicated, but that is a deduction. I make a deduction. The opposite way is an induction. You have a premise that's believed to be true, and you use that to obtain a specific conclusion. For example, in a deduction would be looking at the entire month of July's high temperatures and say it's hot in July. Induction would be I know it's hot in July, and therefore on July 15th it's probably going to be hot. Again, it doesn't have to be 100% true, but that's my deduction. Here's another example. Some people with arthritis or whatever other problems, if it's humid out, their knee hurts. So a deduction would be the humidity makes the person's knee hurt. Because it's humid out, the person's knee hurts. An induction would be tomorrow it's going to be humid, and therefore my knee will hurt tomorrow. It's something specific from a general standpoint, whereas a deduction is the opposite. You've got a bunch of individual data points and establish a general rule. Of course, a critical component of any research is information gathering. Information gathering is based, generally speaking, on observations. So the inductive scientist believes that patterns of explanation will become obvious once enough data is collected. The inductive scientist, and again, tries to draw conclusions about specifics from general points. So the idea is once you have enough data, the conclusions will become apparent, whereas the deductive scientist gathers data only within a guiding theoretical framework. The deductive scientist, again, neither of these are right or wrong. It's, different ones will apply to different situations, but a deduction looks for specific data points in order to draw general conclusions. Looks for data within a guiding theoretical framework. I'm looking to determine whether it's hot outside. I'm looking to determine whether there's an effect of humidity on the knee. I'm looking to look at the general rule that I can apply to any situation. Whereas the inductive scientist looks at the individual data points as something that can be induced. The individual data points are the end result that I'm going to be looking for, the thing that can be proven. Of course, the problem with induction, which is looking for a more specific data point, is that they may contain assumptions that are invalid. With a deduction, you're looking for general principles that apply to that are gathered from many different data points, whereas induction may require certain assumptions that may not necessarily be valid. And finally, in terms of testing anything, there has to be a chance at falsifiability. Falsifiability is a concept. It sounds kind of weird that something has to be falsifiable because we want it to be true, but in order for something to be established as a scientific theory or a scientific law, it has to be capable of being proven false. If something is not capable of being disproven, well then by definition it's not capable of being proven either. For example, if I say that there's a little invisible man inside your refrigerator who turns on the light when you open it, but that person cannot be detected, well, it can't be proven true, and it can't be because it can't be proven false. It can't be tested. If I say that's not detectable, well then how in the world are you going to test it? If you can't detect it, well then you can't detect whether it's there or not. Now I think we all probably agree that this statement is false, but this is an example of something that is not falsifiable. If something can't be detected, it can't be tested, and if it can't be tested, it can't be proven or disproven, and if it can't be proven or disproven, it cannot be something that is the subject of experimentation or the scientific method. In the end, what we're looking for in terms of a conclusion from a series of scientific research is a theory. A theory has the requirement or the function of organization and prediction. Organization is, okay, we can establish a general rule that is now going to apply to other cases, and based on that theory, we can make predictions. If a theory doesn't allow you to make a prediction as to what's going to happen, well then it's worthless. A theory that people who eat big breakfasts are going to be less hungry at lunchtime, that could be a theory. It's a fairly obvious statement, but let's assume for the sake of argument that we experiment on it and we prove it to be correct, so we call it a theory. Well, now this can predict that tomorrow morning, if I have a big breakfast, it's more likely that I am going to be less hungry by lunchtime. Again, that doesn't necessarily mean it's true 100% of the time. Many, especially in psychology, these things are not going to be 100% one way or the other, but it is more likely. I can predict that it's more likely that something is going to happen in accordance with the theory than against the theory. Data that's inconsistent with the theory, if over the next 26 days we test it and experiment it and realize that people who ate a bigger breakfast are not necessarily going to be less hungry by lunchtime, well, then that could lead to a rejection of the theory. And of course, good theories explain a variety of occurrences with only a few statements. They should be simple, they should be precise, and of course they should be testable. Simple means people, when I said less hungry is actually not very precise, not very testable. Let's say I have a theory that people who eat big breakfasts are, 25% more likely to say that they are less hungry at noontime. That would be something that's much more precise. That would be something that's testable, whereas just a general idea of less hungry or more hungry may not be testable. An intervening variable, later on, this is very similar to the concept of confounding that we're going to look at later on. But an intervening variable is something that can interfere with the theory, even though the theory is otherwise valid. For example, an intervening variable could be the mid-morning snack that people have. Maybe the idea is, maybe I've got a theory that, or I establish a theory that people who eat bigger breakfasts are going to be less hungry at lunchtime. But on the other hand, what if I fail to account for the fact that people who have smaller breakfasts tend to have bigger snacks in the middle of the morning, and therefore that's going to kind of neutralize the idea? Well, that's an intervening variable. Or let's say, for argument's sake, I say that people who have bigger breakfasts are likely to be bigger people and therefore have a stronger hunger. These are things that when I'm testing, I have to try to make sure to eliminate these intervening variables in order to make sure that I come up with results that are going to be reproducible. A parsimonious theory, a similar concept to something called Occam's razor, which you might have heard of. Parsimonious theory is something that's based on simplicity. It's a theory that explains a wide variety of constructs with few explanatory constructs. In English, a wide variety of occurrences with few explanatory constructs. In English, that means something that a theory that it's based on the simplest explanation of something. Just the idea that the simplest explanation is going to be the most likely explanation. That's this idea of parsimony. Let's say a person walks in and just played tennis and says, "I'm really tired." Well, let's examine why you're tired. Well, the simplest explanation is, the person could be tired because the person's sick. The person could be tired because they didn't get enough sleep last night. There could be a million reasons why the person's tired, but the most simple explanation is the person is tired because they just finished playing tennis. That would be an example of just applying the most basic explanation to something until that explanation, of course, could be proven incorrect. A theory, if it lacks precision, it can be misinterpreted easily or misapplied. That's why a theory has to be precise and has to be specific in order to really be scientifically valid. And then we finish up this chapter with the idea of research. Research is the method by which people gather information to test it or to establish hypotheses or to establish theories. If a theory can potentially be disproved later, in other words, we don't know whether it's true or false, but it cannot be tested now because the organization doing the testing doesn't have the money, or because the infrastructure isn't proper for testing it now, the evaluation can be postponed until it can actually be tested. Research in hard sciences like biology, physics, things like that is similar to the research in soft science, even though gathering data might be a lot harder in the soft science. Psychology is considered a soft science because things can't be proven so easily. The fact that people become a little bit more depressed or a little more angry or a little more withdrawn based on various factors that happen in their life, it's not as easy to measure those things. Those things can be measured, or else this discipline wouldn't exist and this course wouldn't exist, but they can't be measured as easily as, in physics, how fast something falls from a building. It can be measured with precision. The reason why somebody's depressed, or exactly how depressed the person is, or how excited the person is, or how manic the person is much more difficult to quantify and to establish than hard sciences are. Basic research is research to come up with general theories and rules rather than specific applications. Again, as we discussed before, basic research as opposed to applied research. Applied research is to come up with specific information that can be used, whereas basic research is to come up with general theories. So, for example, or it may eventually, basic research may be used to establish applications that are useful, or it may never. A study to determine whether or not an automatic process can interfere with a more resource-demanding controlled process. The idea, in other words, the question of whether a robot can learn to have human judgment. Well, that in itself could be basic research, and then if the answer to that is yes, well, then maybe down the road there can be applied research to determine whether you can put a robot on an assembly line to build a car, or something to that effect. That's the idea where basic research can just to establish principles, and those principles can later be used to establish applications. And finally, this is similar to what we discussed before. In order for an experimental result to reflect a particular process that occurs in the real world, in other words, in order for it to be reproducible, in order for it to be something that you can apply to real world situations, you want to try to control to eliminate other potential contributing factors. You want to try to make sure that the group that you experiment on simulates real life situations to as close a degree as possible. And in future chapters, we're going to discuss that in more detail as well. Chapter 3 is about articles. We are going to look at just some very basic ideas about databases, parts of an article. We're going to look at graphs and charts and the roles that they play, and some basic information before we get to the more complex stuff in further chapters. First of all, of course, research databases, and there's a whole bunch of lists of research databases over here, are places in which people who are interested in psychology or other sciences as well can go to get information regarding whatever it is they're looking for. Obviously, one way you can find something out is to do the experiment yourself and to use the scientific method yourself. Another way you can find things out is look at what other people have discovered when they've tried these same things. If you have a question, odds are pretty good that somebody else has had that question before, and somebody might have done the research for you. So you've got many different possibilities to look at. There are psychological abstracts, which are printed in the database of psychological research. They can be helpful in crafting studies. These may not be full articles. They may not be long articles that take a long time to read, but they may be a single paragraph or a single page of discussions and studies so that you can kind of look through them, kind of skim through these a little bit before you decide what you want to read in a little bit more detail. It's a lot better than reading every 100-page article out there before you determine which one is actually relevant. You've got Psycinfo, which is a type of index. Index is about 2,500 journals of psychological research. Obviously, that can be very useful, and because it gives you access to a whole bunch of different possible databases. You may not automatically have access to this. Some of them are from pay sites. Some of them are from journals that you may have to purchase, but at least you can see what has been reported. You've got the Social Science Citation Index, which gives the most recent findings on a given topic in psychological research, and the APA, or the American Psychiatric Association Publication Manual, or the American Psychological Association, whatever it is, discusses the various publications that are relevant to articles that are important in psychological research. And one reason why this is important is because whenever you talk about an article, you want to make sure that you're able to consider the source of the article before you actually make a determination as to whether it's reliable. And that's because experienced researchers tend to pay attention to the author of the journal, because they may know the author and his or her biases or tendencies. If you happen to know, for example, that an author does not believe in a particular scientific theory, let's just take one controversial issue, let's say like global warming. Most scientists believe that there is a problem of human-caused global warming. There are a small minority of scientists who don't believe it. So, for example, if you see an article saying, "Oh well, last year really wasn't so hot, we don't have to worry about it," but you know that this author is famous for writing many stories in the past denying the influence of humans on global warming, then you may want to take it with a grain of salt, or at least make a determination about how much credence to give it. And that's of course because even good researchers and good authors may have some biases. Just because a person's biased doesn't necessarily mean that what they're saying is false, but it does mean that you may have to do a little bit more research than you ordinarily would before you take the word of that individual. A journal article title should be short and to the point, and should give an indication as to what the article is about. Titles are usually not just 2 or 3 words like novel titles are, but they're, usually 10, 15 words, something like that, that give you a little bit of an idea of what it's about, but don't give too much away. The most common form of a title is short and gives reference to the dependent, not defendant, the dependent and independent variables, but does not usually give away the finding. So for example, a study, sorry, again, typo there, I'll fix it right now, a study of the effect of rain on the moods of chimpanzees. It's short. It tells you what the thing being studied is, in other words, the independent variable, which is the effect of rain. Then, sorry, there seems to be a lot of typos on this one, we'll fix them now. The mood of chimps is the dependent variable, is the effect that is being tested, and it doesn't give away the result. It doesn't say, rain decreases the mood, or rain makes chimpanzees upset, or something like that. That would give it away. Titles could do that, theoretically. There's no inherent reason why they wouldn't, but generally speaking, they don't. If you want to know what effect the rain has on moods of chimpanzees, read the article, or at least read the abstract, because the abstract will very often tell you what the article tells you in the end. The abstract at the beginning of the article is a paragraph, or 2 paragraphs, summarizing the key points of the research, and unlike the title, the abstract usually will give away what the article's conclusion is. It'll give you kind of a short synopsis of it, and you can read that and make a determination as to whether you want to read the paper. Aside from the abstract, in other words, in the article itself, you've got the introduction, which explains the hypothesis, provides a summary of the relevant research, and does not necessarily discuss the results. The results are held for a little bit later on. But in other words, the hypothesis is, of course, what the problem is and what your theory is. The problem might be what impacts the moods of chimpanzees, and then your hypothesis might be that rain makes chimpanzees more depressed, or rain makes humans more depressed, or cold weather makes people less happy, or whatever your hypothesis is. And then it explains what research you did. We took 100 people, and we put half of them in a rainy place, and we put half of them in a sunny place, and then came back a couple of days later and tested them by asking them questions that was designed to elicit about their mood. And that's, of course, also in the methods section. You're going to discuss more about the research methods used, the participants, how many you used, the procedure you used, the materials. Again, you're not discussing the results necessarily, but you can discuss more and more, tell the reader more and more about how you conducted this experiment and why you chose various things. Why did you choose 50 participants and not 100, or not 200, or not 1,000? Was it because you didn't have the money, or because you thought that 50 would be plenty of people for reasons X, Y, and Z? Then you've got the apparatus section, similar to the method section, but it explains the details of materials used in the conduction of the research, including any new technology. Is there something that other experimenters can use that you found out would be good for a particular type of project? Okay, the method section, as we discussed before, can include the process for participants. How did you select the participants? How did you come to choose people? Did you just look them up in a phone book? Did you put in an ad asking for people to come and volunteer? Instructions given to the participants. What did you tell the participants? Design features of the experiments. Again, doesn't go through the results. You have the procedure in terms of how the experiment was done. We had the whole apparatus set up, we had the whole method set up, and then we gave 50 people the questionnaire on day 1 before we put them in the room with the rain or without the rain, and we asked them questions about their mood, etc., etc., etc. Then you have the discussion section, and then of course you have the results section. The discussion section is the analysis of the procedure and results. And this, when you read it, this is the thing that you can read with the most skepticism, because this is something that is not really based on fact. In the method section, you may agree with the method or disagree with the method, but this is what's happened. This is the fact. This is unless you think the writer is lying to you. There's nothing really to debate. There's a debate about whether the methods were a good idea, but you don't have to worry about what actually happened. The analysis, on the other hand, the analysis is, oh, okay, we concluded that people, we saw that people answered the question yes after they had been in the rain for 3 days, and the question was, do you want to go to sleep or whatever, and therefore we concluded that people are in a bad mood. This is the sort of thing that you might want to look at with a little bit more skepticism, because maybe you disagree with the results, or maybe you disagree with the interpretation of the results. And the reader tells the results section tells the reader what the results are, includes graphs, charts, tables, statistics, not raw data, which is what you started the experiment with, like how many people you brought in, but this is something that you show the reader the data that shows whatever theory you're trying to establish. A very important component of papers, of research papers, all types of research papers, textbooks, etc., are graphs. In a graph, and I'm going to move this over a little bit over here, hopefully you can see everything that needs to be seen. You have two components of any graph. You have an x-axis and a y-axis. An x-axis is typically the horizontal axis. For example, in this one it would be the temperature axis. If this is a line graph to show how tomato temperature affects tomato plant growth, the x-axis is this axis, and the y-axis is the vertical axis, the one that goes up and down. You've got two different variables that you put in here. Typically, the independent variable goes on the x-axis, and the dependent variable goes on the y-axis. In other words, the independent variable means the thing that you're testing, the thing that you want to know its effect, goes on the x-axis. In this example, what are you testing? You're testing the effects of temperature. So the temperature goes on the x-axis, starting with 10 degrees Celsius and going all the way up through 35 and 40 degrees, which you can't see, but is all the way on this part of the graph. But that's okay. The point is, that is the thing that you're testing. That is the independent variable, so you put it on the x-axis. On the y-axis, you put the dependent variable. In other words, you put, okay, what is it that you are trying to discern the effect on? And in this case, this is a line graph to show how temperatures affect the tomato plant growth, so therefore the tomato plant growth is the thing that is the dependent variable. And therefore this, you might not be able to read it, but this says height of 30-day old plants in centimeters. So this is on the y-axis. You've got the dependent variable on the y-axis. Now obviously, as you can see, this graph shows a slightly positive trend. As the temperature goes up, the height also tends to go up, not by a tremendous amount, but it does definitely show a positive relationship. On the top, by the way, you've got an example of graphs with a little bit more in terms of bells and whistles. Here you've got also time. This is a very simple graph, plant growth in height, in time and height. After a certain period of time, the plant grows. So the independent variable, the thing that is causing the growth, is on the x-axis. On the y-axis is the height. And you can see this actually shows different components. You've got, what did you feed the plant with? And with vinegar is all the way on the bottom, didn't grow much at all. With soda, the plant grew, but not as much as with some of the other things. Then you've got juice, in which the plant grew a little bit higher. Then you've got the control group, which I guess just got water. I guess in this experiment you were testing the effect of feeding plants with juice, vinegar, and soda. So the control one, I imagine, is probably water. It doesn't say it, but that's okay. But either way, you've got 4 different lines over here, and all of these tell you what the effects are, from the time, which is obviously the independent variable, the thing that is causing the growth, to the growth, and then you can show 4 different groups on one graph over here. Okay, so the graph on the right is a line graph, really both of them. There are 2 of them over here, and they're both line graphs. There are other types. There are bar graphs, but they're all essentially the same thing. And this is the best way to visually establish a relationship. You can see right away, without looking very hard, that temperature increases, the tomato plant growth increases as well, and the same thing is true for these various things that you're feeding the plant with. Now, interpreting a graph is also important. A direct relationship means as one goes up, the other goes up as well. That's certainly true over here. As the temperature goes up, the height of the plant goes up. An inverse relationship is the opposite. If you'd have a graph that starts up here and then goes down, you'd have an inverse relationship. As one goes up, the other goes down. Or you'd have no relationship, where there's no discernible trend. No relationship would either look like a flat line, going something like this, which means as the temperature went up, it really didn't have any impact, or it's just like kind of a wild array, like one here, and then 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 one here. In other words, there's no real trend in one direction or another. And finally, in this chapter, a little bit of discussion of articles and papers that are formatted for the American Psychological Association. A reference section in an APA formatted paper. APA is, of course, one of the two major methods by which papers are cited and our materials are cited in papers, the other being MLA, which is the subject of other classes. But an APA should include the most important publication in the research topic areas. The references, in other words, what you cite when you're establishing the proof or whatever it is you're trying to establish, what you cite should include the sources that are as recent as possible and as complete as possible. You want the most recent research and you want the most complete research. Obviously, if you cite everything that was 40 years old, the implication is that things might have changed between now and then, and who says that what you say is still valid? Readers finishing an article should be confident that if they were to run the same experimental procedures, they can expect the same results. That's really the hallmark of a good experiment. A good experiment has to be reproducible. When an experiment is reproducible, that means that somebody else could take the same materials. What you're really doing is training and saying, if you take the same materials and you do the same thing and you take do the same exact method as I do, the method should be clear, then you can reproduce my same results. A reader might ask when reading a paper, what was the author's goal? You want to establish to the reader what your goal was, in other words, to prove your hypothesis. You want to make your hypothesis clear. What's the hypothesis? How would I run the same experiment? And in the method section, in the section where you're discussing how you ran the experiment, the reader should say, okay, what is the independent variable? What are the dependent variable? What are the control variables? In other words, what other groups were kept to establish a baseline of behavior that the effect on the dependent variable could be measured against. And finally, the reader should ask whether any questions were left unanswered. That, of course, is true sometimes in any kind of a study. Nothing inherently wrong with that, but just because the paper discussed some questions doesn't mean necessarily that they're all answered. Our next chapter focuses on a very important aspect of experimentation, and that is the ethical issues that are relevant to experimentation, and also, of course, how those ethical issues impact the reliability of the study. Of course, when researching human participants, it's important to control for mood variation. Starting a depressive mood can be offset by introducing a happy mood. I know it sounds silly, but when people test psychological treatments or drugs, you have to sometimes determine whether it's a cloudy day or it's a sunny day. Research shows that people tend to be in better moods on sunny days, and if the mood is going to impact somebody's reaction to some sort of psychological treatment, you got to try to account for that and try to counteract that. Maybe give them all donuts, I don't know, or something to counteract the mood. In order to be ethical in terms of a study, it's important to get informed consent of the subjects. If you're going to experiment on someone, make sure that they understand that, preferably in writing, that they're going to be tested. Get their consent. This includes, of course, the obligation to explain to participants all salient features, all important features of the research before the experiment is done, and to give them the opportunity to decline participate. If you're in a shopping mall or something and you're trying to get subjects, when they come over to your booth and say, okay, for $10 I'll participate in this, you got to explain what you're testing and what possible impacts this could have. This can also be done after the fact. Sometimes what a person says will be important in the discussion. And if you tape them without their knowledge, which you're really not supposed to do, but if it happens that their voice happens to go on tape and you want to use that as part of it, getting them to consent after the fact is fine. Sometimes participation in an experiment can be an academic feature. If you're going to participate in this class, if you want maybe a higher grade or if you want to pass this course, sometimes if you're in a psychology class, you might be asked to participate in some sort of experiment. However, from an ethical perspective, it shouldn't be required. Students should have an alternate means to meet the course requirements. In other words, the professor can say, you can participate in this study, but if you don't want to participate in this study, you can write a paper instead or something like that. It's really unethical to kind of coerce somebody by saying you can't pass the course unless you do X, Y, Z. That really is a little coercive. It doesn't really give the people the opportunity to decline. There are, of course, many other ethical guidelines, which I'm going to list. Many of these are fairly self-explanatory, but we should still go through them. Informed consent should be obtained if the research setting is not benign, which means if it has the potential to be dangerous at all. Confidentiality concerning the participants' results should be maintained. You should not, of course, just like any other treating physician or treating psychologist, a person, whatever a person says or whatever a person does, should not be revealed to a third party. The researcher is obligated to undo any potential harm. Even if the person was informed, if a person becomes sick or if a person becomes depressed or whatever it is, and the researcher can undo that damage, obviously it is the ethical thing to do in that respect. In giving people money to participate in studies is done, and there's nothing inherently wrong with it, but giving a very large incentive is of questionable ethics. The idea is that you don't want to influence somebody's behavior in the experiment by doing something that's really seriously alters their motive. Giving somebody a nominal fee of a couple of $100 for their time over a few days, that's probably not a big deal. But to give somebody a tremendous amount, it kind of taints the study a little bit. Some studies do require deception of the participants. An example we discussed before of giving people a placebo. If you're testing headache medication, you give some people the actual medication and some people a placebo. They think that they're getting the medication. Well, that's deception, but there's nothing you can do about it. It's part of the experiment. Sometimes there is so to say that you can never deceive the people being experimented on would kind of negate the entire purpose or the entire effectiveness of many experiments. So the researcher has an obligation to claim the true nature of the experiment, or to tell really the true nature of the experiment. I'll say disclose the true nature of the experiment after the test is over. As it turns out, you got the placebo. Deception should be minimized, and deception is really only acceptable if it's necessary to the study and if it doesn't harm the participants. If it's not headache medication, if it's bacterial, if it's a treatment to if it's penicillin, if it's a treatment to cure a bacterial infection, to not cure someone, to not give somebody antibiotics, and to give them the risk of contracting rheumatic fever or something because they're not taking their penicillin is really that's obviously not ethical. Important information about an aspect of the experiment should not be omitted unless absolutely necessary, same idea, and of course participants should be allowed to withdraw from the study in progress for any reason they want to. That's another ethical requirement of a study. If the participant gets uncomfortable and wants to change their mind, they can do so. Participants, of course, should be as voluntary as possible. The best way to participate is to run an advertisement and let people choose to come in. If that's not always possible, sometimes you won't get enough volunteers and you have to go to your class, you're a professor and you have to go to your psychology class to get, quote unquote volunteers. Sometimes that's necessary, but the best thing to do is to really get people to be as much volunteer as possible, and putting an ad in the paper saying if you want to come in, that obviously is going to get you volunteers. It is acceptable to detain a participant longer than scheduled in order to ensure safety, because the safety of the participants is a responsibility of the researcher. That includes even if you signed a waiver saying I know I might get hurt or I know I might get sick, it's still the responsibility of the researcher to try to make sure that no danger comes on the people being the subject of the study. Sometimes for example, if somebody is being subjected to some sort of a drug that makes a person lightheaded, well, then of course it's perfectly ethical to keep the person in the room, make sure the person doesn't leave and drive home until the effects of the lightheadedness has gone away. And of course, the responsibility of the ethical behavior doesn't only apply to the person conducting the study, but also the editor and pretty much everybody. The journal editor, if I'm writing a study, or I'm doing a study to be published in the New England Journal of Medicine, well, if they know that I conducted the survey in an unethical manner, and they publish the result anyway, well, they're really contributing to the unethical behavior. So the responsibility is to all the people involved in the process of distributing the effects of the experiment. Now we come to a fairly controversial topic, and that is experimentation on animals. Now, there are some people who think that there shouldn't be any experimentation on animals and that experimentation on animals is immoral. Generally speaking, the medical community and psychological community as well generally agrees that experimentation on animals can be valid and can be necessary, or I shouldn't say necessary, but justified. So, because animal research has directly led to the development of treatments for a variety of disorders, depression, eating disorders, phobias, drug addiction, you may say, well, hold on a second, do animals really have drug addiction? Do animals really get depressed? Well, they exhibit behavior, they exhibit symptoms that are similar to the psychological conditions in humans, and they can be tested on. And the view that animal research is necessary for human progress is sometimes referred to as speciesism. Racism is when you believe your race is the highest race. Anthocentrism is when you think that your ethnic group is the highest. Speciesism is where kind of your species, namely the human being, is the most important. And some people don't think that's a good idea. Some people think that we have no right to experiment on animals, even to advance human interests, and even some people will go so far as to say that animals have natural rights. Just like humans have natural rights, maybe animals have natural rights also, and by experimenting on animals in a way that can hurt them, we violate their natural rights. However, most experts accept, sorry, that's another typo here, so correcting these, it's good. So by the time you see this, they won't have the typos. Except testing in animals, especially because a lot of animal research directly benefits animals as well. The thing is, if somebody complains that there shouldn't be animal research and they have a dog, well, maybe you can ask them whether they know that the vaccines that their dog received were also tested on animals. It's not just humans that benefit from animal testing; it's also other animals that benefit from animal testing. Recent studies show that there's a decreasing use of animals in research because it's becoming less necessary. Hopefully, if you can test on humans in a way that doesn't cause any harm, you might as well do that. It's always better to test on humans anyway because it's more likely to produce results that are going to be effective on humans. You can test on a monkey or test on a rat, but if you test on a human, you're going to be more likely to get a result that's going to be reproducible on another human being. What about pain stimuli? In other words, introducing pain in animals. That has also been allowed, and that has also been done. It is sometimes used in animal research. After substantial deliberation by the researcher and the Institutional Review Board. The Institutional Review Board, by the way, is the people that, usually the institution, like a college, that's overseeing the experiment or the research, will appoint a board that will kind of oversee the experiment and to make sure everything is being done properly. And after careful deliberation, sometimes they can come to the conclusion that introducing pain in animals is okay. Because essentially it can be justified when it's the only way to conduct legitimate experiments that could have substantial benefits to humans or other animals. I've been involved in, one time I had a summer job, I was involved in research on on animals, and very often it did cause them pain, but it was justified on the idea that this was going to help humans cure or take drugs that were going to help them cure diseases. When using animals in research, there's always an obligation to be as humane as possible. Even if it's necessary to hurt or even kill the animals, it's as humane. Obviously, it should be done with as little pain and as little suffering as possible. There's a need for a trained supervisor. If the animals have to be killed, then they should be killed as quickly and painlessly as possible. There are laws regarding animal usage, and those obviously have to be followed. So, I mean, the idea of euthanasia may sound very not nice, but you have to realize that many of these animals that are being tested, they're not designed to live in the wild. I mean, if you have lab mice that are tested, you can't just take a lab mouse after you're finished with it and throw it out into the forest because it's not going to know what to do to survive. It was born in captivity. It was born in a lab. It's always lived in captivity. If you put it out in the forest, it's going to starve or be eaten very quickly. It's not going to be able to fend for itself. So after you're done with these animals in a lab, there really is no other humane way to, unless you have some sort of a used a used mouse farm. The only real way to deal with them humanely is to kill them very quickly and painlessly. There's of course no guarantee that the animal won't be harmed, and very often are harmed in the course of research experimentation. And again, as we discussed before, APA guidelines do allow experimentation in research that's scientific, educational, and applied as well. One last issue regarding ethics is, of course, the dangerous issue of scientific fraud. Fraud is a type of deliberate bias. I specifically put information into a report or into an experiment that I know to be not true. For example, a researcher could change a few numbers to be more consistent with hypotheses. I want this result to be a good result because I want to be able to publish it in a scientific journal in order to get tenure at my college, and my experiment isn't working so well. So I doctor up the numbers a little bit here and there to make it a little bit better. Well, that obviously is a form of fraud. When identical data correlations are obtained across many different studies, that could be an indication of possible fraud. In other words, if there are many different studies and they all come up with the exact same numbers, you have to realize there's some random chance that could be established. There's some random chance that should cause some random variation. If the same numbers come across over and over again, that could be an indication of fraud. I mean, there was a story I remember, Nate Silver, who runs 538.com, who's a statistician. He was once trying to determine whether a polling company was committing fraud, and he looked at the last digits on their polling results. You'd say a certain candidate got 45.31%, and he looked at the last digit, 0.31%, that one, which is really an insignificant digit, but he looked at that over and over and over again and saw that some digits came up more often than they should, which is an indication that a human being is making up the numbers rather than just them being totally random. Again, you can Google it. It's an interesting little study that he did. If you're interested, you can Google probably. Well, let me find it for you. Okay, here's the article. I found it if you're interested in it. So this is, whoops, this is the article that he wrote about it, and so anyway. This is the URL if you're curious, 538.com/features/strategic-vision-polls-exhibit-unusual. Alright, anyway, you can look at that another time if you're interested. Idea plagiarism is the idea that you take somebody else's idea and pretend it's your own. Closely follow a design that somebody else suggested and don't give that person credit. Now, just because somebody else does an experiment doesn't mean that you can't reproduce it. You can reproduce it, but you have to give that other person credit and say, well, Joe Smith did it first, and now I'm doing it again to see if it still works. Joe Smith did it in 1978. Does it still work in 2015? You can do that, but you got to give Joe Smith credit for it. The responsibility to determine and prevent scientific fraud lies with everyone involved, including the researcher, that institutional review board we discussed before, and the granting agency. And an institutional review board in general, which is established usually by a college overseeing research, should have at least one member from a non-scientific area, somebody who can look at the business aspect or, other academic aspects, and have at least one member who's not affiliated with the institution in order to bring a perspective that's maybe less biased and less interested than maybe the other members on the board. In the next chapter, we're going to discuss observation methods. In other words, different ways that data can be collected, different ways behavior can be observed, different ways studies can be continued when it comes to research methods in psychology. First one is this naturalistic observation or ethology. That essentially what that means is not necessarily conducting any kind of controlled experiment in a lab, but just going out in the world and seeing what happens. This means observing information just by observing general non-controlled behavior. On the one hand, it's hard to get good data because it can be difficult to define a small set of easily categorized behavior to observe. In other words, you don't have really control over what you're observing. The idea here is, you go into a classroom and you see all the children, and then you see how you ask their teacher how they're behaving, and then based on that, you look at what behavioral modification drugs the children might be taking, what kind of homes they come from, their academic performance. In other words, you can do a study, but the thing is, you don't really have control over the variables. You have to kind of work backwards. First, you have to see the children's behavior, and then you have to kind of look for clues in their backgrounds. Now, that can be fine. There's nothing wrong with using a naturalistic observation way of collecting data. That certainly we all do that from time to time. It's obviously not as controlled an environment as an experiment. For example, if you want to know specifically, will a child be tired on a particular day based on having a certain experience the day before? Well, you can't necessarily control when the child has that experience, so you don't really know that you have to kind of get lucky in order to have the confluence of events that you're trying to test, and also you have to get lucky that there are no confounding variables. Remember, a confounding variable is where something else causes a problem. For example, if a child is very tired the day after having this experience that you're testing, well, maybe the child is tired because the child also didn't get a good night's sleep. I mean, it's hard to really control to make sure that there are no confounding variables, but again, that doesn't mean that a naturalistic observation is invalid. It just means it's harder to get really good data from it. It's also, of course, much cheaper than actually controlling the experiment yourself, since the behavior isn't actually paid for or planned, it just happens. Then there's a deviant case analysis. Deviant case analysis essentially is when you look at just real life scenarios also, but you make a determination that, or you have a situation where one gets the treatment that you're looking to test and one doesn't. You're not simulating it, you're not controlling the environment in a lab, but, for example, you have two people that have the same issue, the same psychological issue, and one gets treatment and the other doesn't. That could be because of their choice, it could be because one can afford the treatment and one can't, it could be because of pretty much any reason you like, but then you just study the effects on both people. Comparing notes between the cases to see differences that might explain different results can be used to draw inferences. These are cases in which you're not really using an experiment per se. The next example is also a case in which you're not using an experiment per se. You're asking the people to give you data, and that is by surveying. We've all taken surveys at various points, whether it be marketing surveys or surveys to rate our teachers or whatever it is. A survey is when you collect responses to questionnaires from a group of subjects. You'd like as random a sample as possible. Just like with all experiments and with all data, you want to make sure that you don't have a biased sample. For example, if you only survey, the idea is you're surveying the utility of a new car, and you only survey people who are very rich. Well, then people might not, they may want certain fancy features, such as very powerful and excellent acceleration or anything, whereas other people who don't have that kind of money, might really value reliability and dependability more. So you want as random a sample as possible so you can draw from as broad a spectrum as possible. Now, the way to get people to answer your surveys can be asking for volunteers or by paying people, but again, when you do that, you want to make sure to try to still get as random sample as possible, because people, maybe if you ask for volunteers, maybe you're going to get the people who don't have jobs and don't have other things to do, who aren't busy. People with jobs and families may not have time to volunteer to answer the survey. Paying people to do it is okay also, but again, that you might skew it to people who need the money. You might not get people who make a lot of money or have a lot of money who might not be willing to fill out a survey for $20, whereas somebody who doesn't make much money and makes $12 an hour might be happy to get $20 to fill out a survey. So it's okay. I mean, you can do that. Really, there's no other choice. So you can't, short of forcing people to fill out surveys, there may be no other way to get people to fill out surveys. But when you do, the choice method the way you choose these people should be as random as possible. Again, you can't totally, in general, when it comes to research methods, you can't totally control 100% of everything, but you have to control what you do control. The ecological function of behaviors refers to the function that seems to serve the organism. The idea here is that when you're looking at the adaptability of a person's behaviors, that is something that has to be taken into account with every study. Studies should, and really what that segues to is that studies should be as ecologically valid as possible. In other words, we want to try to simulate a real life environment as much as possible. The extent to which findings of a research study can be generalized to a real life setting that's the more valid it is. The more this is also a key word, this generalized. How well can you generalize your study? Okay, you took a survey that people would want to engage in this behavior or would engage in that behavior. Well, how well can you relate that in real life? For example, if you ask somebody, would you react aggressively if somebody threatens you? Well, if somebody's sitting in a lab or answering a survey, might say, no, I would be nice and calm. Don't worry about it. I'm the kind of person that's not excitable. But then, if you generalize it to a real life situation, the person might not react that same way once their ire is raised for whatever reason. So that's maybe a problem with surveys in general. They're not as generalized as a real life simulation. In a real life simulation, at least you get something that simulates behavior, whereas a survey may not be as valid. Again, that doesn't that doesn't impugn the ability of survey to be useful, but all research methods have their problems, and that might be a problem of a survey, that it might not be as generalizable as as ecologically valid as something that simulates something that happens in real life. Response style could be a problem for a proper survey also. In other words, what kinds of questions are you asking and what kinds of responses are you soliciting? Are you putting people in a position where the way you phrase the question indicates what you want as an answer? The way you phrase a question can be very indicative of what kind of response you get. If you want to ask somebody, would you fight back if you're attacked? And you ask one person, would you defend yourself if you were attacked? And if you ask another person, would you lash out because the other person provoked you? You might be asking a similar question, but the way you phrase it could indicate your response. So you want to try to phrase it as neutrally as possible. Then there's observational research, which is studying people or studying whatever the subjects of your studies are, just by observing. So these provide excellent ecological validity because you're observing real life behavior. The problem with an observational study is they sometimes can lead to anthropomorphizing, which we discussed a little bit earlier, and that is studying non-human behavior, maybe studying animal behavior or studying even inert behavior. People tend to kind of ascribe human characteristics and to assume that human characteristics apply, or at least think of things in terms of human characteristics, whereas observation of non-humans really don't necessarily have any human characteristics. Another problem is reactivity, and that is, even if people are behaving in a real life scenario, if they know they're being observed, they may behave differently. If you are testing somebody's aggression over the course of a month by videotaping them wherever they go, well, people know they're being videotaped. They might be less aggressive and try to show themselves in a better light than they would if there was no camera there. Making unobtrusive observations, in other words, making yourself as invisible as possible so that the subject kind of forgets they're being observed, is one way to try to counteract that. Obviously, making the subject totally unaware that they're being studied is one possibility, but then you run into those ethical issues of non-disclosure. If you put up cameras in a place where people know that there could be cameras, but people don't know that there are cameras, that might be the best way to do it. Participant observation is by going undercover, studying the actions of a target group of people. Police do that to try to see who's engaging in criminal activity, but researchers can also kind of go undercover. If you want to see how people behave in a particular type of environment, like a school, maybe you go enroll in the school and go there for a semester and just kind of be one of the crowd and see how people behave that way. Then there's also the problem of motivated forgetting. which is that people may forget unwanted memories. When it comes to surveys, when it comes to looking at people's behavior, and especially if they're asking them to recount their own behavior, this idea of people kind of intentionally forgetting what they don't like could be also a problem in studying people's behavior. None of these problems are insurmountable. None of these problems mean that these studies are worthless, but they do have to be kept in mind. Advantages to observational research that we just discussed: it can be, as we discussed, it can provide more ecologically valid measures of behavior because it's simulating real life more. It's flexible in their procedures. You can kind of make decisions on the go as opposed to experiments which may be tightly controlled in labs. And of course, it's much less expensive than setting up a lab and setting up an experiment. Response sets is another thing that you need to kind of be worried about when you're asking people about their behavior, because that's a tendency for respondents to answer questions in a way that produces a certain image rather than providing truthful answers. There was once in the early 80s, I think there was something called the Bradley effect, where I think an African American was running for maybe mayor of Los Angeles or some position like that, and in surveys he was doing well, but when it came to polls he didn't do as well. And they speculate it's because when people were answering polls, they wanted to, at least the pollster, to think that they were, racially tolerant and open-minded. But then when it came to actual, in the secrecy of the ballot booth, they changed their mind. One interesting thing they mentioned when President Obama ran for president in 2008 is that didn't happen. Really the surveys were pretty much the same as the actual results. So it was kind of a social commentary that people said that in 20 years or whatever the difference in time was, there was a significant decrease in the Bradley effect in the United States. But this can take the form of response acquiescence, that people want to agree. There's a human tendency in many people to kind of agree with what people are saying. And so people want to agree with the pollsters. They want to sound like they agree with the pollsters to avoid confrontation. Then you have response deviation, the idea that people want to deviate. they want to be argumentative. Social desirability. People want to establish themselves as socially desirable. They want to kind of try to pretend their opinions conform to what they think is more politically correct, so to speak. One possible solution is to force the participants to choose between two equally good or equally bad alternatives. For example, if you're testing gun control, rather than saying, do you think people should carry guns or not carry guns, which maybe sounds like the better answer is to not carry guns, I guess, you can say, is it better to protect yourself, carry protection or carry self-protection or something like that, where people think that, it doesn't sound as bad, so people may be less opposed to revealing their opinion. And again, as we discussed before, conducting surveys can be complicated by the fact that it's difficult and expensive to obtain a representative sample of respondents. You don't just want random people. Well, you do want random people, but you don't just want the first 20 people on the street, because then the sample size could be weighted towards people who live in this area. Or if you take the survey at 7 o'clock in the morning, then maybe your survey is going to be weighted towards early risers, people with people with steady jobs. Whereas if you take the survey in a shopping mall on a Wednesday at 3 o'clock and 3 o'clock in the afternoon, it might be weighted towards people who don't have jobs. But you want to be obviously as random as possible, but you want to grab as much of a cross section of the population as possible. Participants often respond how they think the researcher expects them to respond, that we discussed, and of course reliance on volunteers can limit the generalizability of results. That's one of the problems with exit polls sometimes in political, people are surveyed as they leave the voting booth, as to who they voted for, and people say one of the problems is that the people who stop and answer the exit polls, which could take 20 minutes, are very often people who aren't necessarily rushing to work. A person gets out of the voting booth and has to rush back to work. They're not going to want to sit there for 20 minutes to do an exit poll, whereas people who don't have as much to do might do that. Another thing is that people might not respond. So getting a random sample of the entire population that's available can help, because if people don't respond, at least hopefully the people that don't respond will be from also a random cross section, so the people who do respond will be from as random a group as possible. Now we get into a little bit more of the nitty-gritty of the course, so to speak. We get into a little bit of statistical analysis. Now, thankfully, statistics don't play a huge role in this course. We do offer another course called Statistics, or Introduction to Statistics, which is going to be a lot more complex in terms of numbers and mathematics. Here we're just kind of going to give you the basics. Nothing here. You're not going to be required to know math to complete this course. You're just going to be required to really kind of understand the basics and where these statistical analyses go. Okay, one thing that you see very often in research papers is a contingency table, which is a matrix format that displays the frequency distribution of variables. Frequency just means how often they occur, and variables just means things that can change. In other words, number of successful experiments, numbers of unsuccessful ones. Each cell means the frequency of something, the number, and they're labeled by numbers of rows and numbers of columns. So for example, this, which is, I guess, the number of fish that are eaten in a particular country, I suppose. You got Spain, France, Italy, and I guess that's Greece, although it says Greece, you fine. You got the swordfish, grouper fish, sea bream, sole, etc., and you see these different numbers. Italy, I guess you can see, doesn't eat as much fish, or doesn't have as much fish, whereas the swordfish seems to be doing very well up here. Anyway, or very not well, depending on the case may be. The point, that's not important. What is important is to know that this is an 8x4 table, because there are 8 rows and 4 columns across the top. These numbers are frequencies because they're the frequency of whatever they represent, the number of fish that are eaten, I don't know, whatever. The point is, and then there are 32 total cells, 32 total numbers in here. So obviously this means 30 bass in France and 27 tuna in Italy. Again, whatever those represent. I'm not 100% sure what they represent. It doesn't matter. The point is, this is a type of contingency table that shows you what the contingencies are for each, or how often they occur for each event. Statistical data, in other words, this slide is really more about statistical analysis. There's something called the chi-square statistic. Now, the chi is not. I put an X over here because I couldn't. Well. Anyway, I can't seem to find the symbol over here. So chi it's written as an X, and it kind of has this little squiggly line over here, but for our purposes, it's close enough. Chi-squared is a statistic that determines how far a data set is away from what you expected it to be. You expected it to be 85 degrees, today, and then 86 degrees tomorrow, and 87 degrees the next day, based on historical averages. And we have a data set of 10 straight days, and then we have the actual temperatures based on what we actually observed, and we want to know how far away they are from the median, or how far they are away. And the chi-square is kind of a complex mathematical formula to determine how far something is from what the expected values are. Basically, it helps determine whether the expected values are actually significant. If the data is so far away from the expected values that the expected values are meaningless, that's one thing a chi-square statistic can show. But those are sometimes used. Just again, I'm not going to ask you to figure out to be able to figure it out, but just know what it means if you see it. Ex post facto data means looking at the data after the fact and trying to draw conclusions. This is very often done when you're talking about observations of naturalistic experiments, because you don't really know what you're looking for until it happens, and then afterwards you try to draw conclusions from it, which is obviously a perfectly fine way to draw data, but it may not be a good way to experiment in the first place, because you don't know that you're going to get the data that you need. In research involving after-the-fact assessment of data, the magnitude of reactivity, in other words, how much of the result, if you were told, essentially, if the people knew that they were being studied, reactivity, as we discussed before, could be a problem. Correlation means relationship between two variables. If one goes up and the other goes up, or one goes up and the other goes down, that's considered a correlation. One is correlated to another. Correlation could be very high, or correlation could be very low. A -1 correlation is the lowest correlation possible, and that means for when one goes up, the other goes down. The highest is a perfect positive relationship. As one goes up, the other goes up as well. usually don't have perfect 1.0 correlations or negative 1.0 correlations, but a zero point 0.9 correlation means something is very well correlated. The two quantities are very well correlated. For example, how cold it is in a place and the number of winter coats purchased would probably have a very high correlation. Not a perfect 1.0 correlation, but a high correlation. Whereas how hot a place is and how many winter coats are purchased might have a negative correlation. Again, not negative 1.0, but still pretty low. A positive correlation example, weight decreases as height decreases. As a person, as generally speaking, obviously it doesn't always work this way. There you have short people who are fat and you have tall people who are skinny, but by and large, people who are taller tend to weigh more, not because they're fatter, but just because they have more body mass. And so weight decreases as height decreases, whereas a negative correlation example would be height increases as weight decreases. Now, obviously, in this case, the positive correlation is true, and the negative correlation is not true. But either way, the point is that would be just an example. As one thing increases, the other decreases would be a negative relationship, or you could have no relationship at all. Here are some examples. R equals 0, in other words 1.0 is the highest, negative 1.0 is the lowest, and 0 means there's no relationship whatsoever. Here are some examples. This is a positive correlation, a very strongly positive correlation. This is a negative correlation, not quite as strong as the positive correlation, but still pretty strong. And there are data points all over the place. Obviously there's just no relationship. The data points are just kind of random all over the place. There's no particular line, there's no particular trend for this chart. One thing to remember when you're talking about correlation is that correlation does not necessarily imply causation. Just because two things are correlated doesn't necessarily mean that one causes the other. It could mean that, but it doesn't necessarily mean that. For example, an increase in people wearing boots may be correlated with the increase in carrying umbrellas. More people that wear boots, probably the more people are going to carry umbrellas. They don't cause each other. The boots don't cause the umbrellas, and the umbrellas don't cause boots, but they're both caused by the same external fact, namely the fact that it's raining. So that's an example of two things that are correlated with each other, but are not necessarily caused by each other. They may be caused by the same underlying variable. Now this example is an example where we take it for granted that there is certainly a relationship between smoking and lung cancer, and there is. I mean, it's been proven. But an experimenter doing this research would have to watch out for confounding variables. Now, a study showing a correlation between smoking and cancer could be confounded with other variables. For example, let's say we're talking about stomach cancer or something else, and the study shows that people who smoke are more likely to have stomach cancer or skin cancer, which from a scientific perspective may not be as related, but that could be, just to give you an example, that could be because people who smoke tend to have less healthy living habits. Generally speaking, people who care more about their bodies and care more about their health tend to smoke less. And so therefore, people who smoke might also engage in other behaviors that are not good for their bodies and leaves them susceptible to other illnesses as well. Smoking and heart disease, certainly there is a proven causal relationship between smoking and heart disease, but it also could be, which an experimenter would have to watch out for, it also could be that people that smoke tend to have less healthy habits, and people who have less healthy habits tend to eat more unhealthy foods, and people who eat more unhealthy foods tend to have more heart problems. So that's why a good experiment tries to neutralize the other variables and tries to control for the other variables. Zero correlation doesn't necessarily mean that there is no correlation. If you do an experiment and you don't see any correlation, it could just be because of the range of values is too small. This would be an example of a truncated range. Look at this example over here. In this example, let's say you've got a relationship between foot size and age. Now, if you look at this overall chart, you can see very clearly, you can see a positive relationship. It starts down here, ends up here. Overall, you can see the higher the age, the higher the foot size. But if you only did a study in between the two lines, if you only did a study between age 5.5 and 6.5, let's see if I can zoom in over. Well, anyway, this is the most I can zoom in, so you're going to have to use your imagination a little bit. The point is, what if I covered this whole area and I covered this whole area? Oh, I have an idea. One moment. Okay, there we go. So anyway, this is just a kind of a cross section, a snapshot of that graph that we just saw before, with only the things that we're studying in between the lines. Now, if I only studied between age 5.5 and age 6.5, and I got this data, I might look at this and say, hey, this is kind of random. I mean, I noticed maybe a very, very slight upward trend in some of these, but there's so much overlap that there's virtually no trend. I might look at this and say there is no correlation. Well, the reason why there's no correlation is because I'm looking at it from too narrow a range. When I look at the whole thing, which is over here, I can clearly see a range, but when I look at just what's in between over here, I took too small a snapshot, and I may conclude that there's no correlation when there really is correlation. I'm just not looking at the range very well. In other words, I'll miss the big picture if I only look at what's in between the lines and not the whole picture. So that's why a truncated range, which is a small range, is not good. You want to try to study things in as broad a range as possible. Other issues regarding relationships in data include that a curved graph is also representative of no relationship. Here I can see it went all the way down and then went all the way back up. I mean, I guess there is a relationship, but there's no overall relationship. You can't say there's a positive correlation, or you can't say there's a negative correlation. You may say there's a negative correlation between this point and this point, and a positive correlation between this point and this point, but overall there's no relationship. Actually, the study of if advanced math and calculus, you can actually write there's something called, I'm not even sure if it's a calculus issue, but you can write equations in terms of limits and put the limit from here to here and call that a negative relationship, and the limit from here to here and call it a positive relationship. Then we have really another danger of the covariate. A covariate is a variable that's possibly predictive of the outcome of the study, which can confound whatever it is you're looking for. Whatever you're looking for, it can this can cause whatever it is that you're testing. For example, if you're testing the effect of sunlight on people's moods, well, and so you say, well, if a person is, in July is in a better mood than in January, that shows that the more sunlight is causing the better mood. But on the other hand, maybe the fact that the person doesn't have to go to school in the summer makes the person in a better mood. That's a covariate because it can confound your study by introducing another variable that causes the very thing that you're testing, and therefore makes the independent variable that you're testing maybe not the thing that's causing the reaction in the dependent variable. It can also be incorporated in your study. Maybe what you can do is, in that case, you can test people who you can test another group of people who do have to go to school in July, and you're testing 3 groups, and then maybe you can establish 2 relationships. Maybe you can establish the relationship between sunlight and being in a better mood, and you can establish a relationship between having to go to school and being in a better mood. So experiments can help isolate the variables, and they certainly offer the researcher more control than relational research, because they allow the experimenter to try to neutralize whatever confounding variables there are. Sometimes they say what that means is that the experiment has greater internal validity. Internal validity, as we'll discuss later on, means validity within an experiment. Is the experiment properly done to the point where you're isolating the variable that you're testing as much as possible? Later on we'll learn something else called external validity, which is how well it can be reproduced in the real world. But internal validity is how well you've isolated the variable you're trying to test, to try to make sure that you're only testing the effect of the independent variable on the dependent variable. Okay, Unit 7, or really Chapter 7 over here, is about a little bit more complex than some of the things that we've gotten into so far. We're going to get into comparisons and results. First of all, we've got a concept. This is really more of a logical concept than a scientific concept. Mill's joint method of agreement and difference. And this says if 2 or more cases where something happens have only one circumstance in common, or cases in which it doesn't happen have nothing in common except the absence of that circumstance, then the thing which sets the 2 cases apart must be a necessary part of that result. In English, what that means, if you set up experiments or you set up cases in which you have common facts to both, and in one case it happens, and in the other case it doesn't happen, and there's only one thing separating the difference, then that is what caused the difference. So it snows when it's cold and humid. It doesn't snow when it's not cold and not humid. You could really, those are two factors, but you could go to either one. In other words, let's say you take a day and even let's just say we isolate the cold variable. In fact, I just changed it to isolate the cold variable because otherwise it would get a little confusing. But the point is, let's say you have everything's the same. It's the same city, it's the same humidity, it's the same cloudiness, it's the same precipitation, same everything. In one place it's cold, the other place it doesn't. And the place that it's cold, it snows, and the place that it doesn't, it's not cold, it doesn't snow. Well, then obviously the cold impacted the snow. Now, obviously that's an obvious case. We all know that it only snows when it's cold outside, but in an experiment, the same thing is true, where you take two cases where they're exactly the same, except for in one scenario, you've got a case where it happens, the other case where it doesn't happen. You can determine the reason why you have to have two of them is because one time could be a fluke, but if it happens twice, where it happens in one case and doesn't happen in the other case, when all the other variables are the same, you can establish a causal relationship between them. So the idea of an experiment, very similar to the idea of an experiment, is to produce a comparison between the two circumstances, when the only thing that is different between the two cases is a different level of the independent variable. The control group is used as a basis for comparison and is untreated. In other words, it doesn't get the independent variable. The independent variable is under controlled manipulation by the researcher. In other words, the independent variable you can give a lot or a little or none of it. If you're testing the effect of a drug, well, the control group might not get the drug at all, and then you have one group that gets a little bit of it, one group that gets a lot of it, one group that gets a tremendous amount of it. And the other variables, the person's height, the person's weight, the person's mood, whatever it is that you're worried about confounding the experiment, will be held as constant as possible. And the dependent variable is the one that's not controlled by the researcher, since that's what's being tested. Whether the person's going to get in a better mood or get rid of their headache or whatever it is, that's the thing that is not controlled, because that's the thing you're looking for the result of. You're looking for the effect that the independent variable has on it. Some more things regarding experimentation. A lot of this stuff is review from what we discussed earlier, but we'll still go through it and reinforce these concepts. Of course, it's risky to generalize across species when you do an experiment on a monkey or a rat. That's the idea of anthropomorphization and the general problem that occurs with animal experiments. In experiments, independent variables, as we discussed before, are varied by the researcher to test their effects, and the independent variables should remain as independent as possible from other factors, other confounding variables. So if you're testing the effect of alcohol on driving ability, the independent variable, the thing that you're testing, is the alcohol level, the dependent variable is the driving ability, and the people who are not given, you give one group something to drink and the other group nothing to drink, and hopefully you have a controlled course where nobody's going to actually hurt themselves. That's the control group, the people who don't get anything to drink. Other factors, age, weight, experience, should be as constant as possible between both groups so as to avoid any confounding variables. How about looking at the results of an experiment? Well, if there is not a big enough difference between the results, in other words, the range of levels of the independent variable was insufficient to show an effect, it just didn't show that much of a difference. You fed them whatever it is you're testing and then you had them drive, and the results just weren't that different, then you have a null result, which means no conclusion can be drawn. That doesn't necessarily mean, by the way, that the experiment was a failure. It means that the experiment showed that there's no relationship. That's something, it could be that it shows that your hypothesis was incorrect, but again, that's a perfectly legitimate result. Showing that there's no result, showing that a drug doesn't work, has value also. Now maybe we can stop prescribing these useless drugs. It's important to ensure a strong independent variable by making sure that it will matter in the experiments. So for example, if you're testing the effect of alcohol or food on some person's activity, make sure the person isn't already drinking. I mean, if you're going to test the effect of alcohol on somebody's driving, and the person drinks before they come to the office, before they come to the lab, well, then they may have already been affected before it started. If you're trying to affect whether somebody thinks better when they've had something to eat, make sure when the person comes, usually what you'll have is you'll have two people take the test. One of them will be fasting for the day. They might be taking the test at noontime. One of them had a really good breakfast, and the control group may not have. Actually, I'm sorry, the control group. Well, I guess you could look at it either way, but the other group, the one that doesn't have the food, you'll have them fasting, or at least not eating, or at least eating very little, rather than having eaten a nice breakfast before they came to before they came to the lab in the first place. Then a couple of other quick factors that I want to go into regarding experimental results. And first thing is a floor effect, and that is that the data gathering instrument has a lower limit to data values that it can reliably specify. And that is the idea that you're testing something in a manner that is going to make your results seem insignificant because there's too much of a variable on it. I mean, the only way I can really describe it is by giving an example. You give a test. You're testing the effect of a student studying on a test. You're testing the effect of a student's I don't know how much, well, whether they ate a good breakfast, and you're testing their effects on the test. But you gave a test that's too hard. So the students are all getting a bunch of 50s and 60s, or less. The students are getting everything wrong. Well, then it's really hard to differentiate between the class members because everybody got hurt by the difficulty of the test. If you're testing whether studying helps, then you give everybody a test that just kills them, and everybody fails anyway. It's just the question of whether it's a high fail or a low fail. Well, that's not a very good experiment, because what you did is you gave everybody such a factor that made everybody score low to make it harder to differentiate. I mean, yeah, you can differentiate between a 56 and a 60, but it's much better to have a medium strength test, so that hopefully the people that got enough sleep, or that did enough studying, or that had enough food will get a 90, and the people that didn't will get lower. Conversely, you could have a ceiling effect, which is the opposite. Participants do too well on a task to observe meaningful differences in behavior. You give a test that's too easy. You're testing the ability of people to do something on a full stomach, but then you come in and you ask them a bunch of arithmetic questions, and everybody gets them all right. Well, then your hypothesis may have been right. I mean, your hypothesis may have been right that people are going to do better on a full stomach, or that people are going to do better on a good night's sleep, or whatever you're testing, but you messed up by making the test so easy that it just made it very hard to distinguish between the results. The idea is you have to give something, test people, or test animals, or whatever it is you're testing, on something where you're going to establish a range of performances. The old hypothetical that, or the old thing that people do, where they put a person, or a hamster or something, in a maze and see how long it takes them to get from one side to another, and then put another hamster in there that's had a lot of soda or alcohol or whatever, to test the effects of these things. Now the problem is, if the maze is too easy, they're all going to do it regardless, and if the maze is too hard, none of them are going to do it. And you've had a ceiling or floor effect, and you've kind of nullified all the work you've done on the experiment. The control variables are potential independent variables that are held constant. In other words, a controlled variable is something that you want to make sure is the same because you don't want it to impact your experiment. When you're testing the ability of somebody of alcohol on somebody's ability to drive, you want to keep driving experience constant, because driving experience could also have an effect on somebody's ability to drive, and that's why you want to try to keep it constant. But in a different experiment, they might be an experimental variable. For example, if you want, you could also have a different experiment to test how much experience helps when it comes to driving. So if you're testing a drug's effectiveness for hair loss, age is a controlled variable. If you're giving them all Rogaine or whatever it is you're testing, you want to make sure they're all approximately the same age. They're all, let's say, 60 years old. In another study, you may choose to use age as the independent variable. You may choose to have a 60-year-old and a 70-year-old and an 80-year-old and see which one loses their hair the fastest. That is something that it's a controlled variable in this experiment, but it could be an independent variable in a different experiment if that's what you're testing. A variable that inadvertently causes an experimental result, in other words, you by mistake took people of different ages, well, that is a confounding variable. It's confounded with the independent variable. There's an example here, a Coke Pepsi challenge, where labels had the effect and confounded the effect of the taste. People they wanted to give people a taste test, and so they gave them the soda, but as it turns out, people who one of them had a better label. And the one that had a better label, people thought, or people it got into people's psyche that it tasted better. So that's a confounding variable. That's why when you really do a taste test, what you should do is put them both in the same exact cups, and and don't tell them which is Coke and which is Pepsi. People are going to have preconceived notions, or people are going to have, you know. They're going to be impressed by other factors that are going to confound your variables. The other option, if you have more than one variable, is to actually do a multiple variable experiment where you can have two different variables that you're testing. For example, you want to do Coke and Pepsi. Well, instead of just testing taste, you also want to test the effect of the label. So here you give both people you give all the subjects, the bottle with the label on it. And so now, when you ask them which one is better, you're testing for the effects of both the taste and the label. Now, of course, you want to keep all the other variables constant. You want to make sure that they both have the same level of thirst, and they're both approximately the same age, and they're maybe approximately the same weight. I mean, you want to obviously keep all the other variables constant, but you might be able to test multiple variables with one experiment. Now, of course, the advantage is that it's cheaper to do, or less time consuming to do it at once than to do it in two totally separate experiments. The disadvantage is, of course, that if somebody says they like Coke better, you don't know whether it's that they're liking the label better, or that they're liking the taste better, or some kind of combination thereof. And that's why, as we'll discuss later on, you might try all four possibilities. You might try one person might get the Coke with the Pepsi label, and the other one might get the Pepsi with the Coke label, and the other might get the Pepsi with the Pepsi label, and the fourth might get the Coke with the Coke label, and then you can kind of mix and match your results and figure out trends and figure out what the best combination is, and so you can do multiple variable experiments, but obviously you can't do it in the exact same way you would do a single variable experiment. Now, the rest of the chapter deals with certain issues regarding the participants themselves, and the first issue is the Hawthorne effect. This is a type of reactivity in which individuals modify or improve their behavior in response to the awareness that they're being observed. In other words, if people know that they're in an experiment to determine whether something quenches their thirst or whatever it is, there's a natural inclination to try to cooperate and to maybe even pretend that something is quenching your thirst when it's really not. An example, people who simulated hypnosis in an experiment engaged in dangerous acts. If people know, you've all seen probably these stage performances where somebody hypnotizes somebody else and then says, behave like a chicken, and the person clucks. But so let's say a person is being tested, knows that he's being tested for the effect of hypnosis. And then and even though the person may not be 100% hypnotized, still the person either consciously or subconsciously wants to almost pretend or act hypnotized because they want the experiment to be a success, or because they think it's cool that that hypnosis works, or for whatever reason. That's the danger of the Hawthorne effect, and it's really a type of reactivity where somebody reacts to the experiment in a way that kind of confounds it a little bit. The apprehensive participant role is kind of the opposite. Is the participant is so concerned about how the experimenter might evaluate the responses that the participant behaves in a socially desirable way. Actually, it's not really the opposite. That is the Hawthorne effect. This is the most important source of reactivity in an experiment, and of course, as we discussed before, one main way to get rid of that would be to not let the researcher know they're being studied, but that might not always be possible. In terms of experimental subjects, you could have a faithful subject, which is someone who responds honestly. That's the opposite of the Hawthorne effect. That's where someone who tries hard to respond 100% honestly to whatever's going on, and this is obviously what you want. You want people who are as faithful as possible and try to, or don't react in a way that they think is being asked of them. They want to react in as natural a way as possible. Using deception on the subjects can nullify the problem of reactivity because they don't know they're being tested. If reactivity cannot be prevented, you can correct for it. That's an interesting way of doing it. You can say, okay, well, maybe you can establish that reactivity will cause a 20% increase in the behavior. Well, okay, so you can set the new baseline at 20%, and you can see if it affected, if the behavior was affected more than 20%. So you can conduct simulated experiments to see how much people react based on this desire to be socially, laudable, socially acceptable. And then you finally have this concept of mundane realism, which is the extent to which an activity or the entire study is similar to an activity or process that one would complete in everyday life. This is the idea. You want to make sure that whatever you're testing is as similar as possible to the way it would happen in the real world. Generalizability, it's really kind of a subfacet of generalizability, which is the way the results of the experiment can be applied to everyday life. But as part of that idea, you want to try to make the experiment as realistic as possible. Just as important as doing a good experiment is interpreting the results correctly. And in this chapter, we are going to discuss results interpretation. Our first concept is construct validity, which is the degree to which a test measures what it claims to be measuring. In other words, how valid is it? Did it actually test what you're trying to test? Did it test the effect of this drug? Did it test the effect of a good night's sleep? Really, this mainly determines how well you isolated the independent variable and how well you tried to minimize other confounding variables. The higher the construct validity, the higher the higher the manner in which the independent variable was actually tested for its result on the dependent variable, the more confidence you can have in its results. Now, random error, of course, can negate construct validity, even if the experiment is sound, which means things could happen just by virtue of bad luck. You could get a whole bunch of people in the experimental group who happen to be happier people, and therefore the thing that you're trying to test the mood on is your mood drug on is going to be ruined by some random confounding variable that you couldn't control, and that's why. If the more times you do it, the less likely you are to random bad luck. So if you do an experiment 100 times, it's going to be a lot less likely that you are impeached by bad luck than if you do it 3 times. So, there are other ways to establish good construct validity. You can make sure to operationally define all variables. In other words, you're making sure to define exactly how everything is being administered. Good protocols. These are all things to improve construct validity. Then there's external validity. Construct validity is really just another way of saying internal validity, a good validity of the way in which the experiment was conducted in taking the independent variable and testing its relationship on the dependent variable. Then you have external validity, which is the ability to apply it to general life situations. And again, the more external validity, the more you can generalize. And as we discussed before, replication of research helps to increase external validity, because if you do it many, many times with people or with whatever you're testing on, it's more likely to occur in outside situations as well. Other types of reliability, well, the first type is something that we already discussed. Internal validity, again, is how well the experiment is done, especially whether it avoids confounding variables by controlling for them, by establishing good control groups that are similar enough to make sure that other variables don't affect the experiment. Experiments are likely to have greater internal validity than other types of study, like case studies and surveys, again, because they have good controls. Other case studies, when you're studying an individual and how that person behaves, you may not have a good baseline of behavior. There may be confounding variables. And the same thing is true with surveys. Surveys, you have issues of people giving answers that to improve their own image of social desirability, like we discussed before. Split half reliability is test reliability that's determined by a correlation between scores of 2 parts of a test. Really, split half reliability is the idea it's usually used when you're talking about tests or surveys. It doesn't really apply when you're talking about experiments. But here is, if you want to make sure that 2 parts of the test or 2 types of questions are measuring the same thing, compare the results. Take all the results of the first half of the test and take all the results of the second half of the test from the same person, and if both halves kind of show you the same thing, the first half of the test asks certain questions to lead you to believe whether the person is schizophrenic, and the second half also does, and do the results come out the same? If the results come out the same, then it seems that the two elements of the test are reliable, or at least they're as reliable as each other. They're measuring the same thing. That doesn't necessarily mean the whole thing is reliable, but it does mean that at least it's consistently reliable throughout the survey. There's test-retest reliability, which is determined by scores from the same test retaken at different times. If you're testing somebody's personality, give that person a test on July 28th, 2015, and then you give the exact same test on July 28th, 2016, if it's really about a fundamental personality, the tests, should be fairly similar. If they score similarly, and if you do this or if you do it with different people, and they score similarly year over year, test is pretty good. If they score very differently, so then it shows that it's too susceptible to the person's mood, it's too susceptible to the circumstances, may not be a very good test. Statistical reliability is when you have a large enough sample size to be confident in the results. You could survey 3 people on the street and 2 of them like spinach more than ice cream, and then you go and say, oh, well, look, spinach tastes better than ice cream. Well, if you did that to 1,000 people, you probably wouldn't get that result, because the point is you want a large enough sample size to make the results statistically significant. There's parallel forms reliability, which is you run the experiment multiple times in slightly different forms, increasing the external reliability. If 5 different experiments of different results all establish that people with a good night's sleep get better test results, you change the test a little bit, you change the people a little bit, you change the type of environment a little bit, you change with the kind of test a little bit, and it all shows the same thing. You're increasing external reliability because you're showing that in different real life situations, which have different, the result still tends to be the same. You do the experiment with the exact same factors 12 times in a row, well, that maybe doesn't show as much about whether it's exportable to real life situations, which may be different than your experimental conditions. But if you try so many different combinations of experimental conditions, it's more likely that you're going to come up with results that are exportable to real life. Random sampling is, of course, a key component of what makes the experiment valid. And what you want to establish is that each member of a particular population has an equal chance of being selected. If you're determining who's going to win the governor's race in Massachusetts, well, you're obviously not going to be able to ask all the millions of people, each person, but you want essentially each voter in the state to have an equal chance of being surveyed. And by random sampling, going through a phone book at random, whatever, obviously you don't want to go through the beginning of the phone book and get all the A's, because there might be confounding variables. Maybe people whose last name starts with A are more likely to be conservative. I have no idea. But the point is, you want them to be as random as possible. I guess the best thing you can do is just take all the phone numbers and spit them into a computer and have the computer, like Excel or something, come up with totally random numbers. You have stratified random sampling, which adjusts the results to conform to the demographic. That's an important thing that pollsters also do. Matching the percentages of males and females is an example. For example, if I know that 52% of all voters in Massachusetts are women, which is probably about right. There are a few more women than men out there in society. So if I say 52% of voters are women, and then I do a survey, and in my survey, of my 600 respondents to the survey, 54% of them were men, and only 46% were women. Well, I might want to adjust it and count the women's results as 52% of my entire result, and the men's results is only 48%, kind of adjusted a little bit to simulate real life voting, just because based on random chance, based on random luck, my survey oversampled men. So therefore I want to kind of correct for that oversampling. And political pollsters do this sort of thing all the time. A lot of argument of exactly, what you should correct for. Should you correct for political affiliation? Should you correct for race? Should you correct for gender? Should you correct for people who voted in the last election? There are interesting debates about what exactly you should correct for and what you shouldn't, but some correction is important to establish reliability. And there's meta-analysis, which is contrasting and combining results from different studies to identify patterns. There were 12 different studies that studied the results of a good night's sleep on various enterprises, various aspects that people are doing. And so you can combine these to maybe show some sort of a trend. Does a good night's sleep help with more mental acuity? Does it help with physical strength? Many different tests can kind of contribute to an overall conclusion. A theoretical construct or a hypothetical construct is something that can be used to, I guess, nullify or decrease the reliability of an experiment based on the idea that you have an idea as to why people react in a certain way. It's an explanatory variable, in other words, an explanation as to why something happened, that's not directly observable. Explaining superior test scores by pointing to motivation when motivation is not being tested. I try to test people's test scores from various backgrounds, but then later on I say, maybe it's not really, maybe my test wasn't good, even though I tested random people, because, in the experiment, when the people were taking the test, they had no incentive to do well. So, I don't know if I can necessarily apply that to real life, because in real life, people want to do well on tests because they want good grades and they want a good job and they want to make money, so they study very hard. Whereas in my experimental test, maybe people just don't care that much. So, how they do in their test, because it's not actually going to affect them. So that's an idea of saying, well, maybe when I'm testing grades, when I'm testing, the effect of a person's background on the person's grades, well, it might not necessarily apply to real life. Maybe in that case, I'd want to do more of an observational study. Then, of course, it's similar to intervening variables because it can confound an experiment. It can confound an experiment by establishing some other independent variable, namely motivation, that may be in part responsible for the test results. Okay, now I want to look into various scales. And this is not really about psychology that much, but this is about how things are measured. And there are four basic... Scale means a list in order, in some sort of order. In some sort of... if I want to list the certain results, what color are the cars on a lot, or how much money do they cost? Let's take cars on a lot to determine that. And if I walk onto a lot, one way I can list the cars is a nominal scale. Nominal scale means things are different, but the difference is not quantified. The difference is there's no number to it. If I list and I say, well, this car is red, and this car is yellow, and this car is green, and this car is blue, and this car is orange, or whatever it is, they may be different on a list. I may put a list by color. Here are the red cars, and here are the green cars, and here are the black cars, but there's no numerical distinction between them. A black car is not a 5 as opposed to a red car, which is a 4. You can order them however you like. You can put red first, you can put black first, you can put green first. That's a nominal scale. It's a descriptive category, but there's no inherent numerical value. You can list people by their gender, you can list people by their color, you can list people by their religion, you can list things by their color, or things by their whatever, whatever the case, by their size. Size actually could be listed in terms of a numerical quantity, but a nominal scale means there's no numerical significance between them. You can't really do an experiment on a nominal scale. You can't say, well, the answer was that it came out red. I mean, there's no measurement to it. It's just listing. The other scales all have to do with value, all have to do with quantity. The ordinal scale, in other words, the next level up in terms of statistics, has both identity and magnitude, which means that it can be listed based on size, and it has an ordered relationship, but the numbers themselves have no meaning other than to provide an order. So the best example here is order of finished in a race. We had a race, I came in first, you came in second, and Jane came in third. Okay, that doesn't really... It tells us a number. It can quantify it. We can have a list, 1, 2, 3, but it doesn't really tell us anything about the relationship between the numbers. I mean, I might have finished the race in an hour, and you in an hour and 1 minute, and Jane in 6 hours. The list itself doesn't really tell us anything. It's an ordinal scale. It has magnitude, it has size, but it doesn't really tell us anything about the relationship between the numbers. relationship between the results. We can't tell from this ordinal scale whether it was a close race or whether the winning horse in a horse race won by a mile. Another higher level is an interval scale. An interval scale does have significance by how much of a difference there is between levels. The interval scale measures identity, like the nominal scale, magnitude, like the ordinal scale, but also in equal intervals, like the Fahrenheit scale. Temperature is made up of each equal temperature units. The difference between 40 and 50 degrees is the same as between 50 and 60 degrees. With the interval scale, you know not only whether the values are bigger or smaller, you know how much bigger they are. If it was 60 degrees on Monday and 70 degrees on Tuesday, you know not only that it was hotter on Tuesday, but you also know that it was 10 degrees hotter. And then if it's 80 degrees on Wednesday, well, you know then it was 10 degrees, another 10 degrees hotter. The difference between the temperature on Monday and Tuesday is the same as the difference between the temperature on Tuesday and Wednesday. But there's no real true proportionate relationship. There's no true zero. You can't define the difference as a percentage. For example, you can't say, well, if it was 100 degrees on one day and 50 degrees on another day, it was twice as hot. The reason why you can't say that is because the zero in the Fahrenheit scale means nothing. There's no significance to zero. In the Kelvin scale, you may have heard of, you may have not of, which is a temperature scale. It starts at true zero, which starts at absolute zero. Zero is the lowest possible temperature. That is in that case, that would actually be what's we'll see a little bit later on called a ratio scale, where you can say if something is 200 degrees and something is 400 degrees, it's literally twice as hot because everything is based on zero. But an interval scale is, you can establish the relationship in terms of how big a difference there is, but you can't really establish anything to. You can't really establish a percentage. For example, let's say you're talking about a race. My example before. I finish at 2 o'clock, you finish at 2:05, another person finishes at 2:08. Well, that's an interval scale. You can say not only that I finished first and you finished second, the other person finished third. You can also say that I finished 5 minutes ahead of you and you finished 3 minutes ahead of somebody else. But you don't know, is that a lot or is that a little? When did the race start? Did the race start at 1:56 or did the race start at noon? If the race started at noon, it was a really close race. If the race started at 1:56, it wasn't a very close race. To really find out what the percentages are, you have to have a ratio scale. This has all four properties: identity, like the nominal scale; magnitude, like the ordinal scale; equal intervals, like the interval scale; and it also has to have a minimum value of real zero. Weight. Person weighs 200 pounds, another person weighs 100 pounds. The person that weighs 200 pounds weighs twice as much. Person weighs 150 pounds, another person weighs 160. The person that weighs 160 weighs, 1/15 more. You can tell, not only can you tell how much more, you can tell as a percentage. Exam score. One person gets a 30 on an exam, another person gets a 60. The person with the 60 got twice as many questions correct. That is an example of a ratio scale. Obviously, the best data would be on the ratio scale. If the data for whatever reason doesn't lend itself to a ratio scale, at least an interval scale. When you get to the ordinal scale and you're just having orders, I guess that could matter to some extent. A nominal scale has virtually no place when it comes to experimentation. A couple of other issues regarding scales. There's the psychophysical scale, which measures the impact of physical stimuli on psychological processes. If you get hurt, does that make you more depressed? Psychometric scale measures skills, knowledge, attitudes, and abilities. It's not so precisely defined because these quantities are harder to measure. So, for example, happiness can be tested from a psychometric perspective, but it cannot really be put on a psychophysical level. So you can have somebody answer, how happy they are on a scale of 1 to 10, they're a 9, but it's not as precise as a psychophysical scale, which can determine, how fast something reacts or something, a numerical relationship. A summated rating scale is the respondent is asked to agree or disagree with a number of statements, and you can have strongly agree, strongly disagree. One example of summated rating scale would be the political compass survey that you can answer to see what your political opinions are. Here's the political compass Let me see if I can put it here. Okay, anyway, so this is just a test that you can take to see what your political views are, and it basically goes through like 50 of these, and on each one you can say strongly agree. Like if economic globalizations are inevitable, it should primarily serve humanity rather than the interests of transnational corporations, and you can say agree, disagree, strongly agree, whatever it is. This is a way very often things are measured in terms of people's opinions, people's attitudes, things like that can be measured very often in that way. Self-report methods can also be used. You can ask people, are you happy? Are you smart? Are you a good driver? Whatever it is. But again, it's hard to verify or hard to ensure that it's reliable. They say that if you ask a random 100 people, how good a driver are you? Are you above average? 90% of them will say that they're above average, which obviously is impossible because only little less than 50% can possibly be above average. But you can still that's one of the reasons why self-reports are not necessarily verifiable or reliable. In Chapter 9, we get a little bit more complex as we look into the various designs of experiments. A lot of these things are going to build on concepts that we learned about it earlier, so hopefully it won't be too complex. Okay, first of all, when you're talking about designs of experiments, you could have, and by the way, a lot of this stuff are going to be based on things that we discussed earlier, and a lot of the things that we discussed earlier assumed one of these designs. And let's go through them. You could have a within subject design, which means you're testing people really against themselves. It's the same group of participants exposed to all different treatments in an experiment. You can have the subject try taking a pill once when having a headache and try not taking it. A different time the person has a headache. I've got a headache, I take it. The next day I have a headache, I don't take it. Well, essentially what I'm doing is I'm serving as my own control. Each subject, you're using the not taking episode as being the control, and the taking the pill episode as being the experimental group. So that's a big advantage in that you're correcting for other variables. You don't have to worry about having a different personality, different weight, different psychological makeup because it's really the same person. So fewer subjects are needed, and of course there's less chance of a difference between groups because it's the same person in each group, same people in each group. That's the within subjects design. Obviously the problems with that are it takes more time, there are various other aspects, and as we'll see a little bit later on, carryover effects could be a major problem for within subjects designs as well. You could also have the between group design, which is really the one that we discussed before, where you have an experimental group that is separate from the control group. This is where you have an experiment that has two or more groups of subjects, each being tested by a different factor simultaneously. You put one test taker in a cold room and another in a hot room to see what the effect of heat or cold will have on the ability of somebody to take a test. Now, obviously, the dependent variable there would be how well they take the test, to the independent variable being the temperature. It, of course, has the advantage of not having the events influence each other's performance. What happens to the person in one room has no impact on the person in the other room, whereas if you had the same person do one after another, they might remember certain aspects of the test, as we'll see. In other words, there's no real carryover effect. The disadvantage is that different subject differences may obscure different treatment effects. In other words, there may be confounding variables between the people. People may have different intelligence, or they may have the same intelligence, but they may have different tolerance for heat or cold. Some people might be affected more by cold than others. You have matching subject designs, which is where you try to get the experimental subjects that are matched as closely as to other people, as opposed to randomization. Now, again, these are not four different types. This is one dichotomy, either within subjects or between subjects. And now we have a different question about what the best way to minimize confounding variables is. What's the best way to try to make sure that you have a good baseline? Well, one possibility is to try to match the subjects, try to get all the experimental subjects that are matched as closely as possible to avoid having confounding variables, getting two equally smart test takers in our hot and cold room, And of course, one problem with that is matching on one variable may cause a mismatch in the other. You get two people who may have the same intelligence, but maybe they have different stamina levels, or maybe they're at different stages of health, or whatever it is. Ideally, what like to try to do is to attempt to perfectly match subjects on relevant characteristics, except for the experimental variable. Try to get rid of all possible confounding variables. Sometimes that's impossible. Sometimes you have to realize you're just never going to be able to match the subjects. So rather than trying to match the subjects completely, the other possibility is to randomize. Especially if you have a large sample size. You have 1,000 people that you're studying, let's say. Just try to pick random people, the most random people you can get. Now, you're not going to have perfect control groups, because if you randomize people, you're going to have some people that are smart, and some people that are stupid, and some people that are young, and some people that are old, etc. But if you have a large enough sample size and you randomize it enough, odds are those factors will kind of balance each other off. You have 1,000 people taking the test in the cold room and 1,000 people taking the test in the warm room. Yes, you're going to have some people in each room that are smarter, and some people that have more stamina, and some people that are less influenced by the cold or the heat. But if you have a large enough sample size and a big enough group of people, hopefully those things will kind of even out. And that's really another way to try to, matching subjects is the ideal, but if that's impossible, randomization is an acceptable alternative. Some other issues regarding design. First of all, you've got this attrition problem, and the attrition problem is that people drop out. People sometimes drop out, or either they drop out or their data doesn't work. It could be because their data can't be interpreted for whatever reason. They may refuse to complete the experiment, or they may mature beyond the developmental stage required for inclusion. If you're testing the effects of Ritalin on children, then maybe the person outgrows that mindset where it would be relevant. One example that was given in the book as to why a particular design was considered flawed was the very famous executive monkey experiment. Long story short, essentially they put in two monkeys, one that had a little button that basically would give them shocks if it wasn't pressed correctly, if it wasn't done correctly, but it was randomized to keep the monkeys from being able to figure it out. If they pressed the button, they got a shock. If they didn't press the button, sometimes they got a shock. And then they'd be able to figure it out in terms of when to press it and when not to press it. But then eventually they'd kind of change it up a little bit to keep the monkeys guessing. And they took one set of monkeys that would just get the shocks randomly, whether they whether they didn't play the game at all, and the others played the game and tried to avoid. They had the power to try to avoid giving themselves shocks, and they did they did an experiment, and they found that the monkeys that had the buttons, the monkeys that had the ability to try to control when they got the shocks, developed ulcers, while the other monkeys, who were getting the same number of shocks, but they didn't get the ulcers because they weren't as worried about it. They didn't have they didn't feel like they had the control, so they didn't worry about it. That was an experiment to show that executives are under higher pressure, as opposed to people who are not executives, that whether their company fails or does well is really beyond their control. And the reason why this was disqualified, at least to some extent, because the potential selection bias for how likely the monkeys were to make the avoidance response. Essentially, they were tested in a way that did not properly control for that possible difference in selection bias. Another way to prevent selection bias, or another way to prevent, confounding variables, is to counterbalance. Essentially, controlling order effects in a repeated measures design. This is used within subject designs to distribute order effects evenly across treatments. In other words, what you're trying to do is make sure that there are no differences between the times in which they are established. Here's an example. Again, without an example, it's hard to understand in the abstract. When testing whether exercise or chicken soup is better for a cold, have some people do one first and the others try the other first. The idea is that if you're trying a within subject design, the first time I have a cold, I'm going to exercise. The second time I have a cold, 3 months later or 5 months later or whatever it is, I'm going to have chicken soup. Well, there may be these carryover effects that I remember from last time. Maybe my second cold is not as bad, whatever it is. So what you do is you have some people do the chicken soup first, and some people do the exercise first, and kind of vary the orders. And varying the orders, you'll try to minimize whatever negative effects there are. If it's completely counterbalanced, that means all possible orders are used. There may be 3 or 4 different things you're testing, and you may try different variables. Of course, it's best when there are only a few conditions, and the order is expected to affect the dependent measure. If the order matters, then it's of course very important to counterbalance by trying different orders and see if that makes a difference. That kind of segues to our next issue, and that is the Latin square design. The Latin square design is where you have a bunch of different factors that you're testing, and you try to test them all by varying the orders. If you have 4 different factors, then there may be 16 different orders. If you have A, B, C, and D, you could have A, B, C, D, A, C, B, D, A, D, B, C, and, well, if there's 4 times 4, there would be 16 different possible orders. And what you try to do here is try to establish where each thing is tested in every order. This is used where the researcher wants to control the variation that's related to rows and columns in the field. Rows and columns, of course, symbolizing the different impacts of different variables over here. Each treatment precedes and follows every other treatment equally often. So in my example, where there are 4 dependent variables and 4 independent variables, in other words, 4 possible results and 4 things that you're factoring into the equation, you'd really have to establish the experiment 16 different times. And for that reason, obviously, it's much more expensive and time-consuming to run, since you have to run it so many more times. Treatments are assigned at random within rows and columns, each treatment once per row and once per column, and of course they're equal numbers. And the idea, of course, is to establish all of them. You take all these different groups. In this example, you have 4 different possible orders. This would be an example of a 2-by-2 experiment. 2 possible dependent variables and 2 independent variables. And so you want 4 different orders. So you randomly take, in this example, you have, 20-something different subjects. And you take a random subjects and groups and put them into different variables. The group 1 does, which is subject groups 3, 8, 9, 14, 18, and 22, does first A, then B, then D, then C, and you mix it up so that you've got 4 different possible orders over here in terms of B, C, A, D, C, D, B, A, etc. Okay. Then you have this idea of the experimental group versus the placebo group, and we don't have to spend a tremendous amount of time on this because we've already covered it in previous chapters. The control group is also sometimes given a placebo, which is something that the person is not actually being tested, the person is not actually getting the medication or the treatment or whatever it is, but the person thinks that he or she is getting the medication. So the treatment-specific demand characteristic effects are not tested in the placebo group. I think I'm getting an aspirin, but in fact I'm just getting a sugar pill. In a good experiment, there should be active control conditions that make everything the same in the placebo group and the experimental group except for the thing being tested. Both of them are kept in rooms that are relatively dark, maybe rooms that are relatively cool, not doing excitable activities, and that way when you test aspirin versus a sugar pill in terms of whether it cures the headache, you'll have a relatively good experiment. The control group doesn't receive the level of interest of the independent variable. Of course, the experimental group does. And the idea of the control group is to provide a baseline, to provide the effect of just the sugar pill, in other words, the effect of the psychological influence of taking the drug. How much does that help? And the experimental group, you want to see how much it helps beyond that. Then you have something called a mixed design. A mixed design is where you have 2 independent variables. Here, participants are randomly assigned to different levels of one independent variable and participate in all levels of the other independent variable. Here, basically, you're trying to test both the effect of darkness and the effect of aspirin on headache medication. Now, both of them might help. Darkness might help the headache go away, and aspirin also might help the headache go away. But you want to test either you're trying to test the effect of darkness itself, or you're trying to test, does the aspirin work better if it's dark out? Or does the aspirin work equally well whether it's light or dark out? In other words, you're trying to not only test both independent variables, but you're trying to test whether there's any mixture of results, whether there's any confluence of results between the 2 independent variables you're testing. So what you want to do in a mixed design experiment is you want to give everybody all groups, uh, you want to establish all different possible combinations to see what happens. For example, you might want to have one group with aspirin in a light room, another group with aspirin in a dark room, another group with placebo in a dark room, another group with placebo in a light room, and that way you can look at all four groups and see, was there which one had the greatest effect, and was there a difference between the aspirin in the light room and the aspirin in the dark room, or did the aspirin work equally well? You might find, for example, that in the light room with no aspirin, with the placebo, was the worst, and then the dark room with the placebo was a little better, but then once they took the aspirin, they both got cured anyway, so the dark room and the light room made no difference. That obviously could have an impact in what you suggest to the patient. Do you suggest the patient, okay, go lie down in a dark room and take an aspirin, or do you say take the aspirin and the light or dark won't matter? Okay, so of course the problem, and then the last thing over here really, if the thing being tested will have a permanent effect on the user, it's better to use between subject designs, in other words with different groups, than within subject. Within subject, remember, means when you're using the same person in different times. And the problem is the carryover effect. The carryover effect means that by the time you do the second test on the person might not be in the same position that he or she was in originally. I mean, an extreme example would be, if brain damage was caused by the first variable, then the second, especially in animals, the second variable won't be testable at the same way. One example on human experiments that's very common regarding carryover effects is amount of practice. If you put a person in a maze and you say, okay, listen, we're going to have a between subjects, within subjects design, and we're gonna first give the person a cup of coffee and see how they go through the maze, and then later on we're going to give the same person a cup of whiskey and see how the person goes through the maze. You want to test to see whether caffeine does better than alcohol. Now the problem is that the person might remember the maze, and so the second time around, the person might have a training effect or a practice effect and be able to do it better just by virtue of that, which had nothing to do with the independent variables. And even if you change the maze up a little bit, maybe a person will now have more experience in solving mazes. If you ever go to one of these corn mazes or whatever, even if you do a few of them, you go to a different corn maze, you still might be better at it because you have a better sense for how things are, and in general, those can confound variables. A within subject design, of course, is better when there are large individual differences. If you are establishing an experiment and you know that different people have very, very different characteristics with regard to this issue, then you might want to try a within design experiment, because at least then people can control for themselves. So in other words, there's no particular rule about which is better, within design experiments, or between subject design experiments. But the idea here is that they each have their advantages and disadvantages. When you have a within subject experiment, watch out, make sure you have enough time to do them both, obviously, but also watch out for training effects and carryover effects. And when you're talking about between design experiments, between subject experiments, make sure that you control for all possible confounding variables. Or or you can do both. If you have a subject that both has carryover effects and differences between your subjects, try them both and see if you can neutralize those by using both types of experiments and comparing your results. Chapter 10 mixes certain aspects of statistics with some of the experimental concepts that we've been discussing recently. Factors, or factorials as we're going to call them for the most part, are basically the idea of multi-factor experiments, which are designed to evaluate multiple factors set at multiple levels. There's one thing about whether you took the aspirin, but another thing of how much aspirin did you take, and did you take one aspirin, or did you take two aspirins, or did you take one Advil, or did you take two Advils, or did you take one Tylenol, or did you take two Tylenols? And was it, did you have a headache, and did you also have a sprained foot, and maybe a backache too? Which ones helped for which ones, and which combinations? All of that stuff is the focus of a factorial experiment, and a full factorial experiment is where each factor is tested at each level in every possible combination. It studies all paired interactions, can be economical and practical if there are a few factors. If there are a lot of factors, it may be virtually impossible to test that many different experiments. But if there are only a couple of factors, if we're talking about just 3 drugs and 3 maladies and maybe 2 or 3 different possibilities of dosages, maybe you can do a full factorial experiment. Obviously, the number goes up exponentially as additional factors are added. If instead of just 3 pills, 3 possibilities, you're also testing a leave and also I don't know, alcohol or whatever it is. Now all of a sudden you got 5 factors to test. And remember, for each one of these, you're going to have to test different dosages and different maladies that it's trying to cure. You could run up and you could have an impossible situation. If you have 3 things that you're testing by 3, that's only 9 possibilities altogether. 5 by 5 is 25 possibilities. But if 5 by 5 and then another 5, because you're testing 5 different possible dosages, well, now all of a sudden you're talking about 125 different combinations, and it becomes virtually impossible. The advantage of a full factorial experiment, of course, is that it enhances similarity to the complexity of behavior. What you're doing is you're combining different factors and different combinations, just like in real life. There are many different factors that determine people's behavior and people's reactions to things. It has ecological validity and generalizability in terms of the way it can be simulated in real life, really for the same reason. And it also increases internal validity because you're testing all the different possibilities by testing all these various combinations. So that's really what factorial is. In a simple factorial experiment, let's say a 2 by 2 factorial experiment, where you have 2 possible independent variables, each of which have 2 possible conditions. Did you take the medicine or did you not take the medicine? Did the headache get cured or did the headache not get cured? Actually, that would really only be one variable. So let's say you're testing aspirin and Tylenol, and the results could be the headache got cured or the headache didn't get cured. So you have 4 different combinations really that you're looking at. So 4 is really the minimum level of combinations in a factorial experiment. I mean, the example would be what we discussed before with aspirin and Tylenol and dark room, light room. So you'd have to test dark room Tylenol, dark room Advil, dark room aspirin, light room aspirin, and light room Tylenol. Or if you want to use the control group, then you'd have to add another layer. So it would really be a 2 by 3 in that case. The factor can be 3 levels also. You could have a 4 by 2 by 4, let's say, like we discussed before. Let's say you're testing nothing versus aspirin versus Advil versus Tylenol. And 2, you're testing light room, dark room. And 4 for 1 pill, 2 pills, 3 pills, or 4 pills. Well, then you'd have really a 4 by 2 by 4 experiment, and you'd really have 32 different conditions. Although actually that one there'd only be 29 different conditions, because for none there'd be no difference between taking 1 pill, 2 pills, 3 pills, and 4 pills. But alright. Actually, well, if you had a placebo, alright, whatever. Anyway, you get the point, hopefully. In a factorial experiment, the number of factors is the number of independent variables, and the number of levels is the number of instances that each independent variable can include in this experiment. Well, the independent variable may be by Advil, but how many different times do you have to test the Advil in terms of dosage? In terms of light room or dark room, how many different times do you have to test this particular independent variable? And the factors, of course, are what are being tested. So, for example, if you're testing the recall of a number of sequences in younger or older people and lower IQ and high IQ people, you're testing how, if I give you a number, 26871. So can you remember that I said 26871? And then I try it with 6 numbers, 293417. It's 293417, I think. Anyway, the point is that I'm giving you this test, and I'm breaking it down based on people I have a group of people who are smart, and a group of people who are not smart, and a group of people who are young, and a group of people who are old. So I'm testing the ages and the IQ levels, which are both, of course, independent variables, and the dependent variables will be how much they remember. So I'll have to use different combinations. It'll really, to be a factorial experiment, I'll have to test a young smart person, then a young person with a low IQ, then an old smart person, and an old person with a low IQ as well. And that will allow me a full 2 by 2 factorial experiment. Then what about interpreting a factorial experiment? Well, when I interpret a factorial experiment, I have to distinguish between a main effect and an interaction. A main effect is when one of the independent variables is shown to have the strongest effect. In other words, when all the aspirin people showed dramatic improvement, but the Tylenol reaction was kind of mixed, I could say the aspirin has a main effect. But on the other hand, you can also have an interaction when both variables are shown to have an effect. If I show, for example, the Advil people with the dark room had the best effect, well then there may be an interaction where the dark room helps or multiplies the effect of the Advil. The great thing about a factorial experiment, since you've got all the different data, you've got every single combination tested, you can now look for patterns and look to see how well they correlate with each other. So interactions in a factorial experiments are independent of the main effects. Interactions mean not only does the Advil work, but does the Advil work better in combination with the dark room? Does Young work better in terms of remembering sequences in combination with high IQ? Does it multiply the effect? Does it make the effect stronger? So when one independent variable has the same effects as all levels of the second, then they are additive and there is no interaction in that case. In other words, if you just say that the smart person is going to remember the sequences to the same degree whether that person is old or young, then the effect of intelligence is an additive effect. It doesn't have an interaction, rather it just adds to the effect to the ability of that person. Here are some examples of some effects that you can get from factorial experiments. This top one, hopefully you can see it, is where there's a main effect, but there's no interaction whatsoever. You can see over here that variable A, whether it was A1 or A2, didn't really matter, whereas the B made a huge difference. Whatever was, let's say the A variable was the light or dark room and the B variable was the Advil or nothing. Well, B1 had a 15 regardless of what the A was, and B2 had a 7 regardless of what the A was. This is a B main effect, but there's no effect of A, there's no interaction whatsoever. Here there's both an interaction and a main effect. B made a difference whether it was B1 or B2, but it made a huge difference in combination with A. Look, in terms of when factor B1 was 5 or a 6, whereas factor B2, when combined with A2, drove it all the way up to a 17. So there's kind of a multiplication of effect between A1 and A2, which really manifested itself when there was a B2. Food sometimes, when individually they might not have that much of an impact, but when combined, liquors, whatever it is, sometimes they can have drugs, drugs with liquor. Liquor might make you a little tired, and Ambien may make you a little tired, but liquor combined with Ambien could have a much greater effect than either one could have by itself. That's what they call an interaction. If you look at these charts, let's say you had two factors over here, and you see here there was no correlation between the two. Whatever happens with this one on the x-axis, the y-axis isn't affected. B, there is an additive effect, but there's no interaction. There's a direct relationship, but you can see the two things have nothing to do with each other. They're parallel to each other. One thing has nothing to do with each other. The third one over here is an inverse relationship. As one goes up, the other goes down. 4 shows an interaction, where even though with the first criteria being tested there's no effect, when the second criteria is being tested there is a proportional relationship. The condition that produced a flat line must have had some variable that neutralized the effect of the independent variable to the other one. In other words, whatever experiment produced this one, remember these lines are each of a different experiment, and so this experiment produced no relationship, whereas this experiment produced a different relationship, so therefore the factor, there had to have been some factor that neutralized the relationship between the two, or there has to have been some sort of interaction between the variables to cause it's something like this one. It's this D chart is something like this chart over here, where under B1 there was very little distinction between A and A2, whereas under B2 condition there was a huge difference between A1 and A2. Here's where you have a main effect for both. This is an example where just both, like the aspirin works and the dark room works very well. They both have a tremendous effect, and you can see where the effect is marked no matter which one you use, but they just add to each other. A1 and B1. Let's say that represents no aspirin and light room, so the headache doesn't get helped very much at all. If you have a dark room, let's say A was the aspirin. So A, you have the aspirin, but you have a dark room. You have a light room. That's B1. You have some effect. No aspirin with dark room, you have some effect. But if you have both, you have even more of an effect. That's where both have a main effect. In other words, both increase the effect on the dependent variable, and they really do so independently. That's not really necessarily an interaction. It's just that they both do so independently. An experimenter tests whether people prefer ice cream or cookies for dessert. Study shows that a majority always prefers ice cream, but in the summer there's even a larger majority for ice cream. So there's a main effect that people like ice cream more than cookies in general, but that is magnified in the summer. For example, during the winter you might go to 20 people and ask them, and maybe 12 prefer ice cream and 8 prefer cookies, but in the summer maybe that's 19-1. It's an interaction between the two factors that causes the extreme results. You can also have random group designs. Random group designs occur where comparable groups of individuals are formed, and the groups are treated the same way in all respects, except that each group receives only one level of the independent variable. This is a classical control group experiment. This is really much more within the kind of experiment that we've really been discussing throughout the entire course. And what we do here is we assign each incoming participant. A person signs up, walks in, give them a card, and say, okay, go to room 1, go to room 2, go to room 3, and assign each incoming participant to the next available condition until you have an equal number of each condition. That's really what most experiments do. These are, of course, between subject designs. You're going to have one room where the people are going to get the aspirin, and the other room the people are going to get the placebos. And the way you assign them is random. First person to walk in gets the placebo, second person to walk in gets the aspirin, and you keep going. Obviously, the people who are getting it don't know that. And of course, the most important thing also is to control is the equivalence of the group receiving the various treatments. You want to make sure they're both in a light room or both in a dark room. That you want to make sure that they both have had a similar amount to eat or drink. You want to make sure that they're not sick. Obviously, you want to try to keep all the rest of the factors as comparable as possible. You can also do, as we discussed last chapter, with within subjects design. Which is where you do the same thing on you do the experiment, different components on the people at different times. This requires more measures per subject. In other words, you have to test it on the person at least twice, once with the headache and once without once when they have a headache with the aspirin, and once when they have the headache with the placebo. Again, we've already covered within subject designs already. Carryover effects are the major problems, as we discussed in the last chapter. Then you could have a mixed subject design with at least one within subjects independent variable and one between subjects independent variable. In other words, you have both. You run an experiment with the same person consecutively and with different people. Let's say in studies of GPS systems, I'm sorry, that was a mistake, but in GPS systems, which is obviously global positioning systems, where we get directions, different people were given different qualities of directions and asked to do both familiar and unfamiliar trips. In other words, to figure out how well a GPS works, I think these were in the days when people weren't so familiar with using GPS systems. They were given good directions and they were given bad directions, and see how well the GPS system would help them navigate through the system. Within subject element would be the same people making both trips. And a random group element would be different people given different quality directions. In other words, they also wanted to test to see how well would GPS only work where you're familiar with the territory, or would it also work when you're not so familiar with the territory? So the within subject elements, they took people and they put them in a city where their home is, and then they took them using the same GPS or the same mapping system and put them in an area where they're unfamiliar in order to test them against themselves. Then they would also have different people using the GPS system with similar circumstances. In other words, what you try to do there is you try to minimize the effect of either of the problems. You try to minimize the problem of the mixed design experiments of having different people having different confounding variables, and you try to eliminate the within subjects problem of carryover effects. Here's another example where you have two variables here. You're trying to test whether visual illusions get weaker and weaker as we continue to stare at them. So one variable is the time, the amount of time you stared at them, but also we want to know, is there a distinction between men and women? So you can use separate genders to test between genders, but then if you want to test with the length of time you're staring, you can use the within subject design, because you have two different variables. Now, between genders obviously cannot be tested by a within subject design, unless you're going to change the gender of a person in order to do the experiment, which is probably not going to happen. With gender, the only way you can do it is by having different subjects. On the other hand, when you're talking about length of time, a within subject experiment might be best, because you can have a person staring at it for 3 minutes, and the next day staring at the same thing for 10 minutes, and see if they can identify what's on the paper just as well. The next chapter is going to cover a particular type of experiment, and that is a small n experiment. A small n experiment means a small sample size. Generally speaking, as we discussed earlier in the course, you always want as large a sample size as possible. Sometimes, however, for whatever reason, it's simply impossible. So a small n experimentation can also work as long as we follow some of the rules that we're going to discuss. Small n generally means only one or a few subjects. They're run as individuals, not in groups, because you may only have a few subjects. They may be long experiments, allowing performance to stabilize over time. There was recently a movie that was very highly acclaimed called Boyhood, which followed an individual really from the time he was 8 or 9 years old all the way through college. Now, if you're going to run an experiment like that, now this wasn't really an experiment, it was just kind of a movie that took a long time to film, but if you're going to do an experiment to determine how something happens over time, and it's going to take 15 or 20 years, you're probably not going to get 1,000 people to volunteer to run their lives for the 15 or 20 years with an experimenter following them around. So you may have to use one individual or just a few individuals. The data of each experiment is considered individually and with little use of statistics because there are so few people that are being tested. Examples would be where you're studying behavior modification. It could take months for something to manifest itself. It's much easier to study, something could be easier to study when it's looking at a single subject, if it's very in-depth analysis, or where it could be difficult or expensive to use large sample sizes. Now, there are a few different possible ways to, again, we're talking about usually looking at an individual and how that individual reacts to long-term treatment. Cancer treatment, psychological treatment, whatever it is. Now, there's the A-B design, which is not as good. The A-B design is a two-part phase, which is designed as a baseline, which is the A phase with no changes, and then the treatment or intervention, which is the B phase. You see how a person reacts, how a child behaves in school without taking Ritalin, and then you give the child Ritalin for a few months and study how the child behaves over the next few months. That's an A-B design. The A-B-A design, which is superior, but as we'll see, we can't always use it, shows a reversal to treatment and back again. So in other words, for the child's situation, you'd give the child no Ritalin for 4 months and see how the child's behavior is. Then you'd give the child Ritalin for 4 months and then see how the child's behavior is, and then go back to give the child no Ritalin for 4 months and see if the behavior regresses back to the original point. That's an ABA design. It starts in phase A, then it goes to phase B, and then it goes back to phase A. So the problem with AB design that it's susceptible to confounding. Maybe the child started behaving better because the parents started paying more attention to the child, or because the child grew older, or whatever it is. There's no real way, there's no real good way to know that the reason for the child's behavior at that time was specifically the independent variable. So you need to obtain a baseline of behavior to test the effect of the experiment. You don't know that your original A phase was really a good baseline. ABA, on the other hand, tries to help that. It's called a reversal design. This is the best way to do a small number of small n experiment. And the reason is because what you're trying to do is you're limiting the possibility of a confounding variable. If the child became better behaved because the parents started paying more attention during the B phase, well, then the child shouldn't regress back to the A phase after the Ritalin is taken off. After the Ritalin is taken off, the child, if it were based on factors that have changed, should continue the good behavior. So if the child in the last phase reverts back to the old behavior, it's a pretty good indication that the drug was working. Now, obviously, it's not 100%. I mean, theoretically, it's possible that the parents started paying less attention again as soon as the Ritalin came off. Again, that would be a double coincidence. All that is possible, which is why any small n experiment has some risks, but it's certainly better than the ABA dynamic is better than just testing it once. Now, of course, an ABA is not always possible for various reasons. One reason is that it might be impractical or unethical to take somebody off treatment. If somebody's suffering from cancer treatment and you do an AB phase, and then the B, which is the chemotherapy or whatever it is working, well, then the person's not going to want to go back off the therapy and risk their lives just to help this experiment. So it might not be possible to do an ABA design, and one way around that to help an experiment is to use a multiple baseline. This staggers the treatment to test the experimental variable. Multiple subjects are plotted in a graph where change is made to one but not to the other two. You might have three subjects that are similar, maybe three children that are the same age, or three different behaviors that you're testing in the same child, something like that. And rather than treating them all at once, you stagger the treatments. You start one treatment in January, one treatment in April, and one treatment in June. And then so you have to realize that if there were external variables that were causing this child to change, or causing the environment in which all three of the other children in my first example to change, well, that would all apply at once. If the treatment, if the child A, or the behavior A, which you're treating in January, starts to respond in January, and the treatment that you're starting to establish in April starts to work in April, and the one that you're starting in June starts to work in June, that's a pretty good indication that it's working, and there's not some external factor which just happens to be manifesting itself in these three different staggered months. So this is done when ABA experiments will not work, either because the B phase can have a carryover. I discussed before that it would be unethical to end the B phase if it's really helping the subject, but the other possibility is maybe the B phase can have a carryover. Maybe, for example, the child on Ritalin, when the child is behaving well in the B phase, maybe the child realizes that it's worth it to try to behave well and to make an extra effort, and so therefore going back to the A phase later on might not work because there might be a carryover effect that has nothing to do with the Ritalin itself. So, so one thing you can do is the multiple baseline. This is the best way to nullify a possible carryover treatment. You're using different subjects. You may be using three different children in the same class. It can be used as within subject or between subject. Like I said before, you can use it as three different children. That would be the between subject approach. Or there could be three different treatments for the same problem in the same subject. That would also be within subject, like testing one behavior while the other is being treated. So, if a child has a problem that they're a kleptomaniac and that they have attention deficit, well, you give the drug for the kleptomania in January through June and don't give the attention deficit treatment, and then give the attention deficit treatment in June and don't give the kleptomania treatment. If there was some independent variable causing the child to behave better overall, then you wouldn't see them fluctuate. If you see that the kleptomania goes away during the kleptomania treatment and the ADD treatment behavior goes away during the ADD treatment, then again, that's a pretty good way of doing things, even if you cannot do an ABA experiment, which generally speaking would be a good way to do it. But multiple baseline can also work. We can also do alternating treatment, which is really similar to multiple baseline within subject variable. Basically, you have the small n design with more than one independent variable, like randomly presenting 10 foods with different tastes to the same subject to collect data on the reactions to each of those foods. Here, what you're doing is you're alternating the independent variable. You want to see the person's reaction. So first, you give the person something with sugar, and then you give the person spinach, and then you give the person different things. And each time you're testing the person's reaction. This is an alternating treatment. Now, again, food is not really a treatment, but you can do the same thing with drugs. These most behavioral studies in cognitive psychology are done in this sort of way. Alternating treatments. You give the person one treatment, see how the person reacts, give the person a different treatment to treat a different aspect of the person's personality, and see how the person reacts, etc. The advantage of that is, of course, that it can permit testing of many different types of behavior, whereas your standard ABA reversal experiment only applies to really one behavior, and it also allows both within subject and between subject versions of the experiment. You can do it with different people, as we discussed before, or you can do it with the same person treating different behaviors. Of course, carryover effects are still a problem. Maybe the carryover of the first tested behavior, when you were testing ADD, maybe the drug that tests the ADD also is going to help with the kleptomania, which is going to be your next phase. So you always do have to watch out with, you always do have to watch out for carryover effects like you do in any other experiment that's within subject. Some other issues regarding small sample size concepts. Number one, sometimes you can change the criteria during the experiment. If you're looking for a way to treat a learning disabled child over the course of a long period of time, sometimes after a year or two you might start changing up the treatment. Now, obviously, that's not going to be as good an experiment as to the first treatment specifically, but it might help in the long term determine what the best treatment overall is. Here, it's doing this is used to evaluate the effects of the treatment that's applied in a graduated fashion to a single target. Graduated means you may change the dose. If a person's child's getting Ritalin or whatever it is, you may up the dose or decrease the dose. And that way you can kind of have baselines for different aspects. You can see what the person was getting at 100 milligrams and then see how the person behaves at 150 milligrams. So you have different baselines. Maybe you have a baseline of 0 milligrams, then then you see how 100 works and you see how 150 works. And then you can make a determination of what works best. It's a variation of multiple baseline design, really the same thing, and it shows repeated production of new rates of behavior as manipulations of the independent variable. The behavior would be the dependent variable, and it would be affected by the changes that you're making to the independent variable. A case study is also the idea of a very small n. A case study is basically studying one person. It's the smallest type of small n experiment where you look at the reaction of one person. Many of the things that I've mentioned in this chapter have been really case studies. A small n experiment could be when you're looking at the treatment and its effects on 5 people or 10 people. A case study is simply when you're looking at what happens to one particular individual. There's obviously a huge danger of confounding because you don't know if it's one person. There could just be random luck, or the treatment might not really work. The person might have other factors that are relevant. So that's why you always want a larger sample size. But certainly a case study is better than nothing. Functional analysis of behavior, which means, analysis. How do you make a determination about the behavior of an individual in order to determine whether an experiment is working? Obviously, at first you have to specify the behavior of interest. What are you looking for? You want to define, we learned in earlier chapters, you want to define things as specifically as possible. You don't want to just say the person is nice. That's not good enough. You want to specify what your hypothesis is. What will the person's specific reactions be? Determine the baseline occurrence of the behavior. You want to establish something that would be expected without the treatment or without the independent variable. Then, of course, you want to identify the outcome of the behavior, which is the effect of the treatment on the dependent variable. And you want to make sure that the variables are not manipulated by other confounding variables. Next, we're going to look at an entire group of experiments, an entire category of experiments called quasi-experiments. In quasi-experiments, the only difference between this and a regular experiment is that the experiment lacks a random assignment to the experimental group or the control group. As we discussed before, the general idea is to try to get as random a result as possible, or a randomest assignment as possible, by assigning some people to the experimental group and some people to the control group. In a quasi-experiment, for whatever reason, you're simply not able to do that. One possibility is because you just have no control over who gets assigned to what. For example, if you're testing the effects on things on people who come from violent homes, there's just no way to reliably establish. You can't, for example, go to somebody's home and say, for the next year I want you to have a violent home. You can't do that. I mean, you have to just take your groups as they are. So even though they have poor internal validity and they have poor possibilities of, they have really increased possibilities of confounding variables. People from poor homes may also, people from violent homes may also come from low income homes or low education homes. I mean, there may be other confounding variables that you simply can't control for, but you may just have no other choice. Certainly, again, better than nothing, as we discussed. Treatment observation studies are often quasi-experiments. Remember the ABA model that we looked at last time, where you start with no treatment, and then you have a treatment, then you start with no treatment, then you have no treatment again. These are small n experiments. You may not be able to necessarily get a control group. You may not be able to ideally get a random assignment. Instead, you establish a situation where you're trying to have the person be a control for him or herself at different time periods. But because you don't have this random assignment to a control group as opposed to an experimental group, you don't have the full benefits of having the full experimental design. And of course, you also have the problem of carryover effects that may occur when you're talking about testing a treatment, just like any other ABA treatment observation experiment. A case study is really a type of quasi-experiment. The best thing to do for a one-shot case study, in other words, when you're just testing one individual, is to find a very similar individual who did not receive treatment as a control for the case study. It's not easy to do, and that's why an individual case study is very often considered the worst type of experiment or quasi-experiment. But if you can find somebody from a similar home, who had similar socioeconomic background and did not get the treatment, if you have a new treatment to try to improve the attitude or behavior of an individual, and you find somebody who was in a very, very similar circumstance and did not get the treatment, that's the best way to establish a control. Again, it's not random. It's not like you took two people and you said, okay, one person you're getting the treatment and one person you're not getting the treatment. It's still a quasi-experiment, but if you can find someone who just maybe wasn't part of your experiment at all, just a child or somebody who grew up under circumstances similar to your subject, you can use that person as a control, even though that person really wasn't part of the experiment at all, just by looking at what happened to that individual. Similar to that is the interrupted time series design. This design uses several waves of observation before and after the independent treatment, the independent variable. What this is essentially is looking at many different data points. You have multiple observations before the treatment, multiple observations after the treatment, and in between to try to get an overall pattern The example over here they give is testing the effects of a crackdown on drunk driving by looking at a series of many data points. For example, you might look at the how many drunk driving accidents were there 3 years before the crackdown, and then 2 years before the crackdown, and then 1 year before the crackdown, and then the year of the crackdown, and then the year after, then the year after that, then the third year. In other words, you look at many different data points. If it were just one data point, again, you're trying to increase the validity, even though you don't really have a control. You don't have like in parallel society. I guess theoretically, if you wanted to have a good control, you'd use a different city. You'd use a different city with similar populations and similar culture. If you were testing the effect of cracking down on drunk driving in Boston, maybe you would look to see what happened in New York when they did not have a similar crackdown. So maybe that you could use as a control. But if you can use a control, if you can't use a different city, if you don't have a parallel way of looking at things, you can look at different data points. If you look at things from 3 years before, 2 years before, 1 year before, and then 1 and 2, 3 years after, you can isolate from the possibility of some other factor. If you just looked at the 1 year before the crackdown and the 1 year after the crackdown, well, then maybe you can make an argument that there was something else that caused the distinction. Maybe the economy was better in one of the years, and that caused a decrease in criminality or a decrease in drunk driving, whatever it is. But if you look at many data points, you look at 3 years before, 2 years before, and 1 year before, and then you look at 3 years after, 1 year after, and 2 years after, well, that gives you a better chance of getting a good sample. Of course, the major problem, as we discussed with an interrupted series design, is that it's difficult to establish a matched control group. In fact, you really don't have a matched control group. You're trying to compensate for that by using many different data points. One way to increase the internal validity is to try to include a non-equivalent control, which means that really what makes this a quasi-experiment is simply that the assignment to the group was not random. But that doesn't mean that you can't try to find something that could act as a control, even though you did not specifically have any power over which one was the control. If you're doing an experiment and comparing the effect of a crackdown in Boston to the effect of a non-crackdown in New York, well, you didn't have any control over which one was which, but you can still study that effect. The subject variable is the inherent characteristic that the researcher selects to test its effects that could be something besides the independent variable. For example, if you're testing the effects of education on income, well, obviously the education would be the independent variable, the income would be the dependent variable, but then you might throw other things into the mix. Does age matter? Does gender matter? Does religion matter? Does memory matter? Do these other things matter? And you can kind of use those as extra variables to include in your test. Then we get to the factorial issue that we discussed earlier, but you can kind of just a subject variable is something that's added as a potential variable with an effect to an experiment. Matching is a technique to try to minimize the effect of confounding variables. Really what you're trying to do here is trying to figure out what could possibly confound this experiment. If you're testing education on income, the effect of education on income, well, what might confound it? Well, what might confound it is maybe income of parents. What might confound it is maybe race. What might confound it is age. What might confound it is, there are various other health, intelligence. I mean, these are other factors that could have an influence to mess up your experiment. And so what you try to do with a matching technique is you try to find subjects on both sides who have similar characteristics in terms of all those confounding variables. You try to have subjects that are the same race and the same age and the same intelligence and the same health and the same all that other stuff. That's the matching technique, of course. Problem with matching is, number one, it can be very difficult to do because you got a lot of different confounding variables, and trying to find people with all the same variables is not easy. Measures of some relevant matching variables may be difficult to take. Whether somebody is street smart, for example, can have an impact on their income, but street smarts is not easy to measure. There could be a regression, and we discussed a little bit regression. We're going to really discuss it more next chapter, but regression essentially means that when you measure someone if the result is far away from the average, that could regress and go back towards the average the next day. You take a test on someone and you see that they're extremely unhappy. So then you say, okay, well, if I'm testing some sort of a drug on that person, I'd better find a control who is another unhappy person. But maybe my subject was just having a bad day and will regress to the mean and be a little bit more average the next day, and so therefore my control person won't be a very good control person, because maybe my control person was matched up with the person on his worst day and may not be a good control for the person on an average day. And well, we're going to discuss more regression in the next chapter, but the idea regarding regression in general is that extremes tend to become mitigated. People who are very tall, a person's father is 6'6", the person's probably going to be taller than average, but the person's probably not going to be 6'6". The average height for a man is what, about 5'9"? So a person whose father is 6'6" is probably going to be taller than 5'9", but probably not going to be 6'6", because 6'6" is so extreme that things in general tend to regress towards the average, tend to regress towards the mean. The next generation will tend to be a little bit closer to the general average. Of course, the person could be 6'9" or 6'10". There's no rule one way or the other, but from a probability standpoint, the average is always in between the extreme and the average. So odds are the person will be somewhere between 5'9" and 6'6" in that kind of a situation. Other types of tests include a cross-sectional study, which compares performance across many different characteristics that share a certain characteristic. For example, comparing the running ability of all 10-year-olds to that of all 12-year-olds, if I want to test the effect of age on running ability. Then if a cross-sectional study is, I look at all of them. I don't account for race. I don't account for health. I don't account for weight. I don't account for anything. I just test a bunch of random 12-year-olds against a bunch of random 10-year-olds to try to account for age. Now, of course, a problem with that is that generation or age, in other words, there could be something inherent in that person's environment. For example, maybe 2 years ago the nation was more into running than they are now, so that people who are 12 years old, when they were developing their skills, they did it in an environment that's more friendly to runners. Another example is in politics. 60-year-old people tend to be more conservative than 30-year-old people, so you might say, oh, well, look, older people are, there's something inherent about being old that makes you conservative. That's what some people say. But then other people might tell you that no, because the reason why 60-year-olds are more conservative than 30-year-olds is because 60-year-olds grew up 50 years ago in a much more conservative society, whereas 30-year-olds grew up 20 years ago in a much less conservative society. Opposite of cross-sectional is a longitudinal study, which is gathered for the same subject. Instead of looking at how fast a bunch of 10-year-olds run versus how fast a bunch of 12-year-olds run, you take the person when he's 10 and have him race, and then take that same person 2 years later when he's 12 and have him race, and compare the results to each other. Again, that's very similar to the within subject design. In terms of politics, you take the same person when he was 30, and then take that exact same person and resurvey on the same questions when the person's 60. Well, then you can that's a longitudinal design. The problem with that is that you can confound the time of the test. At least in this case, the 30-year-old and the 60-year-old were taking the test at the same time. Here you're talking about people that are taking this political test 30 years apart. Society might have changed. It might not be anything to do with the individual. It might not be anything to do with the age. It might just be it's a different era and people have different attitudes in general. So each one has their strength and each one has their weakness. You have the time lag design, which kind of tries to have it both ways. It examines the response of different participants at similar ages but at different points in time. What you do is, you have multiple subjects that are each 30 years old, but you don't survey them all at the same time. You survey one at this year and one next year and one the next year, and then you do the same thing to the 60-year-olds, so you try to avoid the problem, the confounding variable, maybe they grew up in that particular generation. Maybe they where maybe the 12-year-olds had a maybe all the 12-year-olds had a really good track teacher in 5th grade, so you try to avoid that by having a 12-year-old this year run, a 12-year-old next year run, and a 12-year-old the year after run. Now you're taking 3 12-year-olds from 3 different eras, and you're able to test it a little bit more efficiently. That's a time lag design. Again, it tries to combine the benefits of it tries to take the benefits of the cross-sectional study without the confounding of that eras tend to do. Then you've got the cross-sequential design, which is a combination of longitudinal and cross-sectional designs by following many differently aged cohorts over time. In other words, you're kind of doing both. You're doing a longitudinal and a cross-sectional design by having several different people, but starting at different ages. We're testing a person at age 10 and a person at age 12. Then 2 years later, we're testing another person at age 10, and then that same person 2 years later at age 12. You have many different cohorts, and you try to correct for any for any variances that might be due because of a particular year, or because of a particular generation, or because of a particular age. And in general, if there's an interaction between age and an experimental treatment, that means that age influenced the treatment. So if you see, in your experiment that the 12-year-olds always do better no matter which era, no matter which person, then that's a pretty good indication that it is a factor. The second to last chapter, and the last chapter with really any heavy-duty statistics, is the chapter on scales and mostly regression. Scales, and we discussed this before, is basically how things are measured. Scale attenuation, which is when the scales don't seem to work out too well, when you have results that are too high, too low, or basically too scattered to really work, occurs when results are in clusters around the very high end of the spectrum and or around the very low end of the spectrum. Could be either one, or it could just be both. That's scale attenuation. If you're trying to test how well something is working and you get a bunch of 1s or a bunch of 10s, it means your experiment didn't do very well. If the scale attenuation is too high, that suggests what we discussed earlier as a ceiling effect, which essentially means if you did a test, the test was too easy, whatever you were trying to do was too easy to reach the top, and because all the results are clustered around the top, it makes it very difficult to distinguish between them and therefore to measure any kind of effect that your independent variable had. A scale attenuation at the low end, where all your results are very low, all your results of a test are failing, all your results of a medication is not working, could be because that there is a floor effect, which means whatever you were doing was too hard or pushed results too far down, and again, it's hard to distinguish. Just an example, if you give a bunch of multiple choice questions and people get 25s, well, 25 is essentially the same thing as getting them all wrong, because a monkey would get 25% of multiple choice questions, assuming there are 4 choices. A monkey would get a quarter of them right just by guessing A, or B, 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 B. Scale attenuation problems, of course, can be overcome. One interesting way to overcome the possibility of a scale attenuation is to conduct a pilot research. We discussed pilot research way back at the beginning of this review. And a pilot research is when you do a small program, when you do just you just do the experiment. Your plan is to do the experiment on 1,000 people with a big experimental group and a big control group. But first you do it on 5 people with a 5-person experimental group and a 5-person control group. And just to now one reason to do one of these would be as feasibility, to see if it's expensive, to see people's reactions, to try to measure how attrition, to do it cheaply. But another thing you can do is you can see what the results are. If you do it with 10 people and you see the results are all too high, or you see the results are all too low, you may have to change the test. It's the effect of studying on passing a math exam. If the exam is so hard or so easy that people are getting all 60s or all 100s, well, then you may want to change the test a little bit. And that's something, so even though the pilot study may not tell you what your ultimate results are going to be, may not tell you anything significant, it may give you a clue that your results are going to be generally too high or generally too low to get a discernible pattern. Then we've got this idea of regression. Regression artifacts result in being skewed towards the mean. And the reason for it, and I'm going to discuss what regression is in a minute, in the long term, the more times you do an experiment, the more likely the average is to regress to the mean. So we all know that when you flip a coin, the heads is going to come out. The chances of heads is 50%. The chances of tails is 50%. Assuming it's a fair coin, it's not weighted, whatever it is. Now, if you flip a coin 10 times, you very well might not get 5 and 5. You might get 6 and 4. You might get 7 and 3. You might get 10 and 0. There's certainly a possibility of that. The more you flip, the more likely it is. I mean, again, theoretically, if you flip a coin 100 times, you could get 100 heads and no tails, but the odds of that happening are, infinitesimal to say the least. It would be extremely, extremely low. But the point is that the more you flip, the more likely it is that you're going to have close to a 50-50. You're not going to have exactly 50-50. You may have 52-48 or 55-45 or 53-47 or 50-50. The point is, the more you do an experiment, the more likely things are in general to regress to the mean. In other words, to regress to the average of whatever it is you're doing. The less likely random chance has to skew the results. That's, of course, one reason why it's good to do many experiments. Students who score way below or way above their averages in one exam will likely score closer to their average next time. The reason is, again, because the people that do something that's far from their average, it's probably because of some sort of anomaly. It's probably because of some sort of strange factor that occurred. With the height example I gave before, even though it's normal for people to be, let's say the average height is 5'9". Obviously, it's normal for people to be a little higher, a little lower. Somebody is very tall, somebody's 7 feet tall. Even though they might have genes for good height, that still was probably also partly an effect of some sort of an anomaly, and therefore the next generation may be taller than average, probably will be. The next generation is unlikely to be 7 feet. Because assignment of participants is often based on factors that are outside of the experimenter's control, so therefore anomalous results can sometimes happen at first, but as we discussed before, the more you experiment, the results should regress to the mean. If you test 10 random people, I think IQ tests are generally designed for an average of 100. So if you test 10 people, they may average 110, but if you test 100 people, if you test 1,000 people, odds are the average will dip down towards 100. And by the same token, if your average started with 90, it will also go up towards 100. The more experiments you do, the more likely you are to get a result towards the mean, and that will kind of cancel out. The regressing to the mean will cancel out the confounding effects, the other possible effects, leaving really the only effect, the effect of the independent variable. So starting an experiment with people with high or low results can be invalidated by regression. So because of the fact that the people who had very high or very low results initially, that might not be indicative of what their real results will be. So, this is true in general. Like if you have a study aid, like these bar review courses or whatever, and sometimes it's easy to manufacture good results, even if you're not that effective, by taking the lowest scoring people. If you take all the people that had the most disastrous tests, and you give them your study aid, odds are even without your study aid they would have improved a little bit because they would have regressed toward the mean. They would have gone back towards the middle. The general tendency is for any group of people to regress towards the middle. So let's say somebody would normally get a 75. A normal average student would get an 85. This student is below average, would normally get a 75. Now if the person gets a 75, they're probably not looking to get a test help or test aid because they already got what they know they pretty much deserve, what they pretty much are going to get. But let's say somebody gets a 60 or a 65, then they're going to go out and hire a testing company to help them. Now that testing company is going to help them. Now in the next test, if they turn around and get a 75, the testing company could say, look, you scored 10 points higher when you had us. But it really could just be a result of regression to the mean. It could just be a result of the fact that they moved back towards what their normal average would be. Another example, they say when people go to a doctor, let's say you have these doctors that have these quack cures, the cures that don't really work, but sometimes they can theoretically prove that they do work based on this regression concept. For example, a person comes into the doctor's office and has a bad back, and the back really hurts. And the doctor says all you have to do is close your eyes, wink 3 times, say there's no place like home, whatever it is, go home and your back will feel better. Now, that might actually work more often than you think it would, but not because closing your eyes and saying there's no place like home actually affects your back. It's just because people visit the doctor when they're at their worst, naturally. And generally speaking, in a majority of cases, they would start to get better anyway with no treatment whatsoever. So then, when they come back a week later and say, oh yeah, my back feels better, a lot of that is just regression to the normal states, more so than it is the effect of the treatment. So regression, of course, has to be focused on when you're doing an experiment. It has to be accounted for. So that's why starting an experiment with high results or low results can be invalidated by regression, because some or all of the improvement might just be regression. And regression, of course, means your personal average, not the class average. If you're a B student, you'll regress towards a B, even if the class average is a C. If you generally are likely to get a B on an exam, and you get C's, well then that's actually anomalous, because for you, B is the norm. Theoretically, if all conditions are perfect and there's no confounding variables at all, there shouldn't be any regression. In other words, if there's no luck, if everybody who should get an 80 will always get an 80, well then there's no need for regression. Then, you would never get that 90 in the first place. That would be a fluke. Regression is the idea that flukes, things that are just based on random chance, won't happen a second time, or a third time, or a fourth time, or whatever it is. So that's why random assignments of participants with large sample sizes can nullify regression as much as possible, and experimental reliability increases with replication with similar participants, because the more you have, the more likely you are to eliminate these random chance and nullify the fact that people are going to have results that are far away from the mean. Instead, their average is likely to be towards the mean, and therefore whatever effect the independent variable has can be measured. And so confidence in the reliability of an experimental result increases when the same conclusion is used a different method as well, which also minimizes regression. Sometimes if you use 2 different types of experiments, with 2 different, if you're testing headache medication, one you have a person take it and then go to work, and one you have the person then go to sleep, and then another time you have the person take it and then do jumping jacks or whatever. The point is that if the results occur in all 3 cases, you're more likely to establish that the ultimate result works, of course. Okay, and finally we have this idea of replication. Replication is the idea of replicating experiments and doing them over, just really kind of a segue with what we discussed before, to redo experiments to try to make the results as good as possible, and there are many different types of replication. There's direct replication, which just means doing it again. You do the experiment once, you get certain results, okay, no problem, get a new experimental group, a new control group, new groups of subjects, do the same thing all over again. An example would be administering the same exam twice to the same class. You want to see if it's a good result. The class gets an 84. Now you want to find out whether the class really learned 84% of the material, or was it just a fluke? Was it too hot that day? Was it too cold that day? Whatever. Was there a party the night before? Well, if you do it again, you're likely to either confirm the results or show that the results were a fluke, especially if you do it many times. Then there's systematic replication, which is the attempt to extend a treatment to a different setting, practitioner or client disorders, by varying the conditions or combining them. Instead of you keep trying with the effect of a painkiller of Advil, but you try it in one group of people with headaches, and one group of people with stomach aches, and one group of people where their eyes hurt or their mouth hurts or whatever, or their back hurts. You're using a different type of participant, but of course you're still trying the same underlying independent variable. And then there's conceptual replication, and this is where you're demonstrating the same phenomenon with an entirely new paradigm, an entirely new set of conditions, an entirely new method by which you're testing it. But you're trying to test ultimately the same concept, the same idea, the same independent variable, but you change the nature of the dependent variable. Then you have converging operations, which is similar to conceptual replication, same idea, where you try different lines of investigation, different types of experiment, different approaches that all serve to try to address the same problem. And this tries to eliminate alternative explanations by changing it. By changing everything else, if Advil cured a headache, well, maybe that can be explained by some other factor. But if Advil also cured a backache, an entirely different kind of person, an entirely different era, an entirely different society, well, then maybe that proves that Advil cures pain. And finally, our last chapter is actually quite an easy one, and this is about just some general rules regarding publishing results of psychological experiments and how papers should look. We've actually covered some of this in earlier chapters, but we'll just go through them over here. Publishing results of a psychological experiment. First of all, there's the concept of a running head, which appears in capital letters on the first page of the manuscript and will appear on the top of the published article. Just basically what it's about. There's the abstract, which is a summary that usually appears on the second page. First there's the title page with the running head that will eventually appear when it's published, and then on the second page you have the abstract, which is a quick summary of the experiment and a quick summary of what the results were. Then you have major headings which are centered, and the next page will go through various parts of the research paper, but they're usually centered and they're on top of the section. Research methods, results, etc. are centered. The introduction is not usually started with the word introduction. It just starts the paper and it just goes through the introduction without actually saying that it's the introduction. And then after it's over, in other words, and we'll look at the sections in a minute, but after the full paper, after that you have the references, which are the sources that were cited in the paper. Then you have the footnotes, where you put 1, 2, 3, and then for each part you'd reference specifically what outside source was relevant to that particular claim. Then you could have the author's notes. The author just writes observations and notes about the study. Figures, which are like diagrams and things that show the reader these things. And these are usually in this order. References first, then footnotes, etc. In terms of the organization of the article itself, of course, psychological research papers are based on the APA, the American Psychological Association format. And this goes through various parts of the paper. You have the introduction, which shouldn't discuss too much of the methods or results, but should state what the variables are. It should explain, listen, we were trying to test the results of Advil on curing headaches. We were trying to test the effects of income on SAT scores. Whatever it is, it should say a little bit more than that, but it should basically just explain what the purpose, what the result, what the problem was to begin with, and what the hypothesis was. Then you have the method section. How were the variables examined? How did we set up the experiment in the first place? Then you have the participants section. In other words, how did you get the participants? How did you choose the participants? Were they paid? Were they volunteers? Were they randomized? You have the results section, and the results section discusses what happened when the variables were examined. In other words, what did the experiment, not necessarily the conclusions that were drawn, but what happened. 86% of people who took aspirin reported that their headache was gone within 15 minutes. 93% of people who kept their eyes open and staring at a light bulb and who did not take aspirin and took a placebo reported that they still had a splitting headache 26 minutes after the experiment, or after they took it, whatever. Then you have the discussion, which states what conclusions can be drawn from the results. In other words, okay, what does that tell you? Does that tell you that Advil works? Does that tell you that dark rooms work? Does it tell you that there's a combination, that there's an interaction, that there's no interaction, there's added? In other words, whatever your conclusion is should be stated in the discussion section. Eventually you're going to have a conclusion section at the end, but the discussion section is really when you tell the reader what to think. And this, by the way, is the part that is really subject to the most analysis and subject to the most skepticism. It's one thing to look at the method section, but the discussion section is really the part that you want to make sure that you agree with the author before you take it for granted. Now, in terms of publications, very quickly, in an article, generally speaking, it's important to use consistent terminology. Some people use he, some people use she. You can use he or she, which is what I think the general standard method is today. But switching back and forth is not really appropriate. Singular and plural. If you want to refer to your subject as being the subject or the subjects, that's okay, but you got to be consistent throughout. A pre-publication draft of the article, in other words, when you first draft the article to begin with, that is a manuscript. In other words, before it's published. Less than 30% of manuscripts are actually accepted for publication, which means that more than 70% are rejected. When it is accepted, but it's not yet published, it is now called a submission, and it can typically take a year or more even to actually get it published, even from the time that it's actually accepted. In addition to the manuscript itself, you can present different things about your study. You can do an oral presentation about an article. You can put it up on YouTube, or you can tell it to your class or to the other staff members and your faculty members in your institution. It should be very brief and not go into as much detail as the written article. Really, it should explain to the people why they should read the written article. And then you have a poster presentation. I have an example of a poster presentation down here, which you can't see it obviously, but it doesn't really matter whether you can see it. The point is, you can see it's fairly detailed. You probably can't read this, but it says introduction up here, and I don't even know what this study's about, honestly. Maybe is there any way to make it bigger? No, I don't think so. But and what this will have, it'll have highlights of the entire article in one sheet. A big advantage of this over an oral presentation is that oral presentation, people would have to sit down and listen to or watch, whereas a poster can just be glanced at. In a poster, you might have a section for the introduction, some quick bullet points of the methods, some reporting of data, reports, conclusions. This is one 4-column thing, and I don't even know what this is about, but this one 4-column thing can kind of give you a synopsis of a 50-page article or a 100-page article, with a couple of relevant charts, a couple of relevant conclusions, etc., etc., etc. And speaking of conclusions, it is the conclusion of this video. So thank you very much for watching. I wish you good luck on your final exam, and have a great day, everybody.